Time is not just something we measure, it is something we move through, something that moves through us. From the heartbeat of a star to the age of galaxies, time flows, shaping everything. Tonight, we follow that flow, from the beginning to the end. In the quiet moments between thoughts, time continues its patient journey. It carves mountains with rain, erodes continents with waves, and paints the sky with stars that lived and died before we ever looked up. Time is the silent architect of everything we see. We measure our lives in heartbeats, in breaths, in the turning of our planet around its sun. But time exists beyond our measures. It stretches back to when the universe was smaller than an atom, and forward to when the last star will flicker and fade. Time gives the universe its rhythm, the steady pulse of pulsars, spinning hundreds of times each second, the slow dance of galaxies, taking hundreds of millions of years to complete a single rotation, the patient birth of stars, condensing from cosmic dust over tens of millions of years. Yet time remains one of our deepest mysteries. Is it something fundamental to reality, or is it perhaps an illusion, emerging from our limited perception of a deeper, timeless existence? Tonight, we journey across time itself. We will witness the birth of stars and their eventual death. We will travel to the edge of black holes where time nearly stands still. We will explore the moment of creation itself and gaze toward the distant future when time might lose all meaning. The universe tells its story through time. Every galaxy, every planet, every living thing exists as a moment in an unfolding tale that began almost 14 billion years ago. We are not just observers of this cosmic story. We are characters within it, made of matter that has existed since the beginning, experiencing the universe through the lens of time. As we drift through space, notice how time shapes the cosmic landscape. In the depths of a gas giant planet, storms have raged for centuries without pause. In the heart of a neutron star, time moves differently, compressed by gravity's unfathomable weight. Near the event horizon of a black hole, time stretches like taffy, slowing to a near standstill compared to the flowing time we know on Earth. Consider the ancient light that reaches us from distant galaxies. The photons that touch your retina tonight began their journey when dinosaurs roamed our planet, or when the first multicellular life was forming in primordial oceans, or even when Earth itself was nothing more than cosmic dust waiting to coalesce. When we look at the stars, we are looking at time itself, unfolded across the vastness of space. Time gives meaning to existence. Without time, there would be no stories, no beginnings or endings, no change or growth or evolution. The universe would be a static photograph rather than the living, breathing film that unfolds around us. Time allows the cosmos to create, to experiment, to learn from its past and shape its future. In our bodies, time manifests as the slow dance of cells dividing and dying, the rhythm of neurons firing, the cycles of waking and sleeping. Your body knows time intimately, from the circadian rhythms that guide your sleep to the telomeres that shorten with each cell division, marking the passage of your years. You are a temporal being, existing not just in space, but in time. Listen to the sound of your breathing. Each inhalation is a moment, distinct from the one before and the one that follows, yet they flow together in the river of your experience, creating the continuous sensation of being alive. This is how time moves through us all, connecting discrete moments into the illusion of continuity. Time also holds our memories, preserving the past even as it creates the future. The patterns in your brain that store your earliest childhood experiences still exist now, carried forward on time's current. In this way, nothing is truly lost to time, merely transformed and incorporated into the ongoing story of existence. So close your eyes, let your breathing slow. As we drift through the cosmos together, following time's gentle current, remember that every moment connects us to the vast ocean of existence. Every second that passes is both ordinary and extraordinary, both fleeting and eternal. From the quantum foam of the earliest moments to the last photon crossing an empty universe, time weaves reality into being. This is the story of how time shapes the universe and how the universe gives meaning to time. Join us as we begin our journey through time, the canvas upon which all of existence is painted. What is time? This question has echoed through human consciousness since we first looked up at the moving stars and wondered about our place in the cosmos. Time exists as both our most intimate companion and our greatest mystery. In our daily experience, time seems straightforward. It is the passing of moments, the ticking of a clock, the rising and setting of the sun. We feel it in the rhythm of our heartbeats and in the changing of seasons. Time appears to flow in one direction, carrying us from past to future through an ever-present now. But beneath this simple appearance lies profound complexity. Time is not a thing we can touch or hold. We cannot slow it down or speed it up. We can only measure its passing and feel its effects. For thousands of years, humans believed time was absolute, a universal heartbeat that pulsed identically throughout all of creation. Isaac Newton captured this view in his Laws of Motion, describing time as flowing equitably without relation to anything external. In this view, time was like an invisible river, carrying everything in its current at exactly the same rate. This perspective served science well for centuries, allowing us to predict the motions of planets and the trajectories of objects with remarkable accuracy. But as we peered deeper into the fabric of reality, cracks began to appear in this simple view. The first hints came from electromagnetism, when scientists discovered light always travels at the same speed, regardless of how fast the observer is moving. This seemingly innocent fact would transform our understanding of time forever. In 1905, a young patent clerk named Albert Einstein published his special theory of relativity, revealing that time is not absolute but relative. Einstein showed that time can flow at different rates depending on relative motion and gravity. Two events that appear simultaneous to one observer might occur at different times for another observer moving at a different velocity. Imagine two identical twins. One remains on Earth, while the other travels through space at nearly the speed of light. When the traveling twin returns, she will have aged less than her Earth-bound sister. This is not an illusion or trick. It is the nature of time itself, flowing differently for bodies in relative motion. Einstein later expanded this understanding with his general theory of relativity, showing that gravity also affects the flow of time. Near massive objects like stars and black holes, time actually slows down compared to regions of space with weaker gravity. On Earth, time passes slightly slower at sea level than it does at the top of a mountain, where gravity is marginally weaker. These differences are tiny in our everyday lives, just fractions of a second over an entire human lifetime. But they are real, and modern technology must account for them. The Global Positioning System satellites orbiting our planet must constantly adjust their clocks to account for these relativistic effects. Without these adjustments, GPS locations would drift by about 10 kilometers each day. Einstein wove space and time together into a single fabric called space-time. In this understanding, time is not separate from the three dimensions of space, but is fundamentally connected to them. We move through time just as we move through space, and the universe exists as a four-dimensional tapestry with time as one of its essential threads. This space-time is not flat, but curved by the presence of matter and energy. Massive objects like stars and planets create depressions in this fabric, causing both space and time to bend around them. When objects move through curved space-time, they follow these bends, creating what we perceive as the force of gravity. Yet as profound as these revelations were, they still portrayed time as continuous, flowing smoothly from moment to moment. But when scientists began exploring the quantum realm, the smallest scales of reality, they found time behaving in even stranger ways. In quantum mechanics, time becomes grainy and uncertain. Particles can exist in multiple states simultaneously until measured, seemingly stepping outside the normal flow of cause and effect. Some quantum processes appear instantaneous across vast distances, challenging our understanding of time's arrow. The physicist Richard Feynman developed a way of thinking about quantum particles that treats them as exploring all possible paths through space-time simultaneously. In this view, particles do not simply travel from point A to point B, but rather explore every conceivable route between them, including paths that seem to move backward in time. These quantum peculiarities have led some physicists to question whether time is truly fundamental or if it emerges from deeper quantum processes. Perhaps time as we experience it is merely a macroscopic phenomenon, arising from the collective behavior of countless quantum events, just as temperature emerges from the average motion of molecules. The thermodynamic view of time connects it intimately with entropy, the tendency of ordered systems to become more disordered over time. When you pour cream into coffee, the two liquids mix together but never spontaneously separate. A dropped glass shatters, but the pieces never reassemble themselves. These everyday observations reflect the second law of thermodynamics, which states that the total entropy of an isolated system always increases. This entropy increase may be the source of time's apparent direction. The past had lower entropy than the future, creating what physicists call the thermodynamic arrow of time. Our memories exist because the past was more ordered than the present, allowing stable records to form in our brains. We remember the past, but not the future, because the future's higher entropy has not yet created impressions in our neural pathways. Some cosmologists propose that the universe's increasing entropy began with the remarkably ordered state of the Big Bang. The universe began in an incredibly dense, hot, yet surprisingly uniform state. As it expanded and cooled, it became more disordered, with matter clumping into galaxies, stars, and planets, increasing the total entropy of the cosmos. This cosmological arrow of time aligns with and perhaps underlies our psychological experience of time's flow. Different cultures throughout history have conceived of time in remarkably different ways. Ancient Greek philosophers like Parmenides suggested that time might be an illusion, that all of existence might exist eternally in a changeless now. Eastern traditions often view time as cyclical rather than linear, with recurring patterns of creation and dissolution. The philosopher Immanuel Kant proposed that time is not a property of the external world, but rather a feature of human cognition, a lens through which we perceive reality, but not an aspect of reality itself. In this view, time is something we impose on our experiences to make sense of them, not something that exists independently of our observation. Modern physics has not settled these ancient debates, but has added fascinating new dimensions to them. Some theories of quantum gravity suggest that at the most fundamental level, time might not exist at all. In loop quantum gravity, space and time are not continuous, but composed of discrete units at the Planck scale, about 10 to the negative 35 meters. At this scale, our normal understanding of time breaks down completely. The physicist Julian Barber has proposed that time is not a dimension in which things happen, but rather a measure of the difference between different static states of the universe. In this view, each moment is a complete configuration of the universe, and what we perceive as motion or change is actually the relationship between these different configurations. String theory, which attempts to unify quantum mechanics and general relativity, suggests that our universe might be a four-dimensional membrane floating in a higher dimensional space. Some versions of string theory propose the existence of closed time-like curves, paths through space-time that return to their starting point not just in space but also in time. These curves would theoretically allow for time travel, though most physicists believe that the laws of physics would prevent such paradoxes from occurring. Time dilation, the slowing of time in strong gravitational fields or at high velocities, has been confirmed experimentally. Atomic clocks placed at different altitudes run at slightly different rates. The clock closer to Earth runs minutely slower than the one farther away. GPS satellites, orbiting at an altitude of about 20,000 kilometers, experience time passing about 45 microseconds faster each day than clocks on Earth's surface. These tiny differences must be accounted for, or our navigation systems would quickly become useless. Near a black hole, time dilation becomes extreme. At the event horizon, the boundary beyond which nothing can escape, time as measured by an outside observer appears to stop completely. An astronaut falling into a black hole would, from our perspective, seem to freeze at the event horizon, never quite crossing it. Yet, from the astronaut's perspective, time would continue normally as they crossed this boundary, experiencing nothing unusual until the extreme tidal forces tore them apart. Our human experience of time involves more than just physics. Psychologically, we perceive time as elastic, stretching or compressing based on our attention, emotions, and activities. When engaged in something enjoyable, hours seem to pass in minutes. During tedious or painful experiences, minutes can feel like hours. This subjective time is as real to our experience as the objective time measured by clocks. Our brains process time through multiple systems: The cerebellum keeps track of precise timing needed for physical coordination. The basal ganglia helps us recognize rhythms and patterns in time. The prefrontal cortex allows us to mentally time travel, imagining future scenarios or revisiting past experiences. These neural systems work together to create our sense of temporal continuity. As we age, our perception of time tends to accelerate. A year to a child seems an eternity, while a year to an elderly person passes in a blink. This effect may relate to novelty and memory formation. New experiences require more cognitive processing, creating more extensive memory traces that make periods seem longer in retrospect. As we age and experience fewer novel events, time seems to compress in our memory. Circadian rhythms, our internal biological clocks, synchronize our bodies to the 24-hour cycle of our planet's rotation. These rhythms regulate sleep, hormone release, body temperature, and countless other physiological processes. They evolved over millions of years to align our biology with the natural cycle of daylight, a reminder that time is written not just in physics, but in our very cells. Time is not a thing we can touch or hold. It is not a substance that flows through the universe. It is perhaps better understood as a relationship between events, a measure of change, a dimension of experience. Time gives the universe its story, allowing change, growth, evolution, and consciousness to exist. Without time, reality would be frozen, static, and perhaps ultimately meaningless. As we continue our journey through the cosmos, remember that every observation we make, every phenomenon we witness exists not just in space, but in time. The light reaching us from distant stars shows them not as they are now, but as they were when that light began its journey across the vast distances of space. Looking outward into the universe is looking backward in time, witnessing the cosmic story as it unfolded across the eons. Time is not a ticking clock, it is woven into the universe itself. In the beginning, there was no time. This statement may seem paradoxical, yet it captures a profound truth about our universe. Before the cosmos existed, before matter and energy filled the void, before space itself had meaning, there was no time as we understand it. Time and the universe began together, twin aspects of the same cosmic birth. Our journey now takes us to that birth, to what scientists call the Big Bang. Not an explosion in space, but the beginning of space itself, the first moment when time had meaning. This journey requires us to set aside our everyday intuitions, for we are traveling to the edge of understanding, where physics meets mystery. 13.8 billion years ago, all that exists today, all the matter and energy in the 100 billion galaxies we can observe, occupied a region smaller than a single atom. The entire observable universe was compressed into an inconceivably hot, dense point, a singularity where the laws of physics as we know them break down. What existed before this moment? This question itself may be meaningless. Augustine of Hippo, a philosopher from the 4th century, recognized this puzzle when he wrote about creation. He noted that time itself is part of God's creation, so asking what happened before creation is like asking what lies north of the North Pole. The question assumes time existed before time began. Modern physics echoes this ancient insight. According to Einstein's general relativity, time is woven into the fabric of space-time. When space-time began, time began. There was no before in any meaningful sense. Stephen Hawking compared this to asking what lies south of the South Pole. The question contains a fundamental misunderstanding about the nature of the coordinates. Yet human curiosity naturally pushes against such boundaries. Theoretical physicists have proposed various models attempting to describe what might have preceded our universe. Some suggest a quantum fluctuation in a pre-existing metaverse. Others propose cyclic models, where universes are born, expand, contract, and are reborn in endless cycles. Still others imagine a multiverse bubbling with countless separate universes, each with its own laws of physics. But these remain speculations at the frontier of human knowledge, where mathematics stretches beyond what we can currently observe or test. What we know with greater confidence begins with the first fraction of a second after the Big Bang, when time, as we understand it, was taking its first infant steps. The earliest moment we can currently describe with some confidence is the Planck era, beginning about 10 to the negative 43 seconds after the Big Bang. This unimaginably brief instant represents the smallest unit of time that has physical meaning in our current understanding. During this period, the four fundamental forces we know today, Gravity, electromagnetism, and the strong and weak nuclear forces were unified in a single superforce. The temperature of the universe exceeded 10 to the 32 degrees Celsius, energies so extreme that our current physics cannot fully describe them. This Planck era lasted only the briefest instant before giving way to the Grand Unification epoch. During this period, gravity separated from the other three fundamental forces, which remained unified. The universe continued its rapid expansion and cooling, though temperatures still exceeded 10 to the 28 degrees Celsius. Around 10 to the negative 36 seconds after the beginning, something extraordinary happened. The universe underwent a period of exponential expansion called cosmic inflation. In an incredibly brief moment, the universe expanded faster than the speed of light, doubling in size perhaps 100 times or more, or space itself stretched, carrying energy with it, smoothing out any irregularities and flattening the geometry of the cosmos. This inflationary period, first proposed by physicist Alan Guth in 1979, solves several puzzles about our universe. It explains why the cosmic microwave background radiation, the afterglow of the Big Bang, appears so uniform in all directions. It explains why the universe appears flat rather than curved. And it explains how regions of space that are now so distant they could never have communicated with each other nevertheless share the same physical properties. Inflation also explains the origin of structure in our universe. Quantum fluctuations, tiny variations in the density of energy, were stretched to cosmic scales during inflation. These almost imperceptible variations became the seeds of future galaxies and galaxy clusters, the largest structures in the cosmos. From time's first moments, the pattern of everything that would ever exist was being written into the fabric of space-time. As inflation ended, around 10 to the negative 32 seconds after the Big Bang, the universe entered the electro-weak epoch. The strong nuclear force separated from the electro-weak force, leaving three distinct fundamental forces. The universe continued expanding and cooling, now filled with a hot, dense plasma of quarks, the fundamental particles that would later form protons and neutrons. This quark epoch lasted until the universe was about 1 microsecond old. As the cosmos continued cooling, quarks began binding together to form protons and neutrons in a process called baryogenesis. During this period, a critical asymmetry developed between matter and antimatter. For reasons we still don't fully understand, slightly more matter than antimatter was created. Perhaps one extra matter particle for every 10 billion antimatter particles. When matter and antimatter meet, they annihilate each other, converting their mass into pure energy. As the universe continued to cool, matter and antimatter particles began finding each other and annihilating. Had there been exact symmetry between matter and antimatter, they would have completely annihilated, leaving a universe filled only with radiation. But thanks to that tiny asymmetry, after most annihilations were complete, a small residue of matter remained. That small excess, that 1 in 10 billion imbalance, is the matter that forms everything we see today, every galaxy, every star, every planet, and every living thing. The first 3 minutes of the universe's existence saw the beginning of nucleosynthesis, the formation of the first atomic nuclei. Protons and neutrons began fusing to form deuterium, a heavy isotope of hydrogen with 1 proton and 1 neutron. Some of this deuterium further fused to create helium, with 2 protons and 2 neutrons. Trace amounts of lithium, the third element, were also formed during this period. For about 380,000 years after the Big Bang, the universe remained an opaque plasma, too hot for electrons to bind with atomic nuclei. Photons, particles of light, could travel only short distances before being scattered by free electrons, like headlights in dense fog. Time was passing, but the universe had not yet become transparent. Then, as the cosmos continued to expand and cool, reaching a temperature of about 3,000 degrees Celsius, a pivotal transition occurred. Electrons could now bind with nuclei to form the first complete atoms. Suddenly, photons could travel freely through space without being scattered by free electrons. The universe became transparent, and light could begin its journey across the cosmos. This moment of transition, called recombination, released the cosmic microwave background radiation, the oldest light in the universe. This ancient radiance continues to bathe the cosmos today, though the expansion of the universe has stretched its wavelengths from visible light to microwave radiation. When we detect this background radiation, we are seeing the universe as it appeared 380,000 years after the Big Bang, the oldest image we can capture using electromagnetic radiation. After recombination, the universe entered a period often called the Cosmic Dark Ages. No stars had yet formed, so there were no sources of visible light. The cosmos consisted primarily of hydrogen and helium gas, gradually clumping together under the influence of gravity, guided by the density fluctuations created during inflation. For millions of years, time flowed as these invisible structures slowly took shape in the darkness. Between 100 and 500 million years after the Big Bang, the cosmic dark ages gave way to the first light. Gravity had pulled enough gas together to form the first stars, massive and brilliant, burning hot and living brief lives compared to stars today. These primordial stars, perhaps 100 or more times the mass of our Sun, fused hydrogen and helium in their cores, creating the first heavy elements and seeding the cosmos with carbon, oxygen, iron, and other elements essential for planets and eventually life. As these first stars exploded as supernovae, they scattered these newly forged elements across space, enriching the gas clouds from which later generations of stars would form. Time was now creating complexity in the universe, writing the chemical diversity necessary for planets like Earth to eventually form. By about 1 billion years after the Big Bang, the first galaxies had coalesced, brought together by the gravitational attraction of dark matter, a mysterious substance that interacts with normal matter only through gravity. These early galaxies were smaller and more irregular than the majestic spiral and elliptical galaxies we see today, but they were the seeds from which the larger structures would grow. Over the next several billion years, galaxies merged and grew, forming the large-scale structure we observe in today's universe, a cosmic web of galaxy superclusters connected by filaments and separated by vast voids. Time was the artist creating this grandest of all structures, using gravity as its brush to paint with stars and galaxies across the canvas of expanding space. About 9 billion years after the Big Bang, in an ordinary spiral galaxy we now call the Milky Way, a cloud of gas and dust began to collapse. At its center formed our Sun, and around it, a disk of material that would become the planets of our solar system. Earth formed about 4.5 billion years ago, a small rocky world in the habitable zone around our average star. Time continued its patient work. On Earth, complex chemistry led to the first self-replicating molecules, then to simple single-celled life, then to more complex organisms. Time allowed evolution to experiment over billions of years, writing and rewriting the book of life through countless generations, eventually leading to creatures capable of contemplating time itself. This cosmic history, from the Big Bang to the present day, represents the unfolding of time on the grandest scale we can observe. But understanding the beginning of time presents profound challenges, both scientific and philosophical. Our current theories of physics break down at the very moment of the Big Bang. General relativity, which describes gravity as the curvature of space-time, predicts a singularity at the beginning, a point of infinite density and temperature where space and time themselves lose meaning. Yet we know general relativity must be incomplete because it does not incorporate quantum mechanics, which governs the behavior of matter and energy at the smallest scales. A complete theory of the beginning of the universe would need to unify these two pillars of modern physics, creating what physicists call a theory of quantum gravity. Various approaches, including string theory and loop quantum gravity, attempt this unification, but none has yet been confirmed experimentally. Some of these theories suggest intriguing possibilities about the nature of time at the beginning. Loop quantum gravity proposes that the Big Bang might not have been the absolute beginning, but rather a bounce, a transition from a previous contracting phase of the universe to our current expanding phase. In this scenario, time might extend indefinitely into the past, with our Big Bang being just one event in an eternal cycle. String theory suggests that our three spatial dimensions and one time dimension might be part of a larger reality with additional dimensions. These extra dimensions could be extremely small and curled up, invisible to our direct observation, but influencing the fundamental forces that shape our world. In some versions of string theory, time itself might emerge from more fundamental timeless quantum processes. The physicist Julian Barber has proposed an even more radical view, suggesting that time does not flow at all. Instead, what we perceive as the flow of time might be a series of static configurations of the universe, what he calls nows, each containing records of other configurations that we interpret as memories or evidence of the past. In this view, the apparent flow of time is an illusion created by our consciousness as it moves from one now to another. Whether time had a beginning remains one of the deepest questions in cosmology and philosophy. If time began with the Big Bang, what caused the Big Bang? If causality itself requires time, how can we speak of a cause for time's beginning? These questions push at the boundaries of human understanding, reminding us of the limits of our knowledge. Yet even with these mysteries, the story of time and the birth of the universe remains one of the greatest achievements of human thought. From careful observations of the present universe, scientists have reconstructed a history spanning nearly 14 billion years, tracing our origins back to the first moments of cosmic existence. This story reveals our profound connection to the cosmos. The atoms in our bodies were forged in the hearts of stars that lived and died before our sun was born. The iron in our blood, the calcium in our bones, the carbon in our cells, all were created through stellar nucleosynthesis, the alchemy of stars transforming hydrogen and helium into heavier elements through nuclear fusion. Time connects us to this cosmic heritage. We are not separate from the universe, but part of its unfolding story. The same processes that shaped galaxies and stars shaped the world that gave rise to us. The same physical laws that governed the first moments after the Big Bang govern the beating of our hearts and the firing of neurons in our brains. As we contemplate the birth of the universe, we contemplate our own origins. The Big Bang was not just the beginning of time and space, it was the beginning of everything that would ever exist, including us. When we study the early universe, we study our most ancient ancestry, the conditions that made our existence possible. Time flows from that singular beginning, through the formation of galaxies and stars, through the birth and death of countless worlds, through the evolution of life on at least one small planet, to this present moment as you listen to these words. All of existence is connected through this flow of time, a continuous thread running from the Big Bang to now. From a single moment, a universe began to unfold. Time is the silent architect of the cosmos. As we journey outward from the Big Bang through billions of years of cosmic evolution, we witness how time transforms the primordial fog of hydrogen and helium into the magnificent structures that fill our universe today. Time does not merely pass in the cosmos. It builds and shapes, crafts and sculpts, giving rise to patterns of breathtaking complexity and beauty. Let us begin with the largest structures in the universe, the cosmic web. When we map the distribution of galaxies across vast volumes of space, we discover they are not randomly scattered. Instead, they form an intricate pattern resembling a three-dimensional web. Enormous filaments of galaxies stretch for hundreds of millions of light years, intersecting at dense clusters containing thousands of galaxies. Between these filaments lie vast cosmic voids, enormous bubbles of near emptiness spanning hundreds of millions of light years. This cosmic web was not present in the early universe. It evolved gradually through the patient work of gravity acting over billions of years. The seeds of this structure were planted during cosmic inflation, when quantum fluctuations in the density of energy were stretched to cosmic scales. These tiny variations in density became the blueprint for everything that followed. In regions where matter was slightly more concentrated, gravity pulled additional matter inward, creating a feedback loop where denser regions became even denser over time. In regions with slightly less matter, material was drawn away toward the denser regions, creating voids that grew increasingly empty. This process, playing out over billions of years, sculpted the cosmic web we observe today. The filaments of this web consist primarily of dark matter, a mysterious substance that interacts with normal matter only through gravity. This dark matter makes up about 27% of the universe, far outweighing the normal matter that forms stars, planets, and living things, which comprises less than 5% of the cosmos. The remaining 68% consists of dark energy, an even more mysterious force driving the accelerating expansion of the universe. Along the filaments of the cosmic web, matter has condensed into galaxies, the fundamental building blocks of cosmic structure. Each galaxy is a gravitationally bound collection of stars, gas, dust, and dark matter. The Milky Way, our home galaxy, contains roughly 200 billion stars orbiting around a common center. But it is just one among hundreds of billions of galaxies in the observable universe. Galaxies come in several primary forms, each telling a different story of cosmic evolution through time. Spiral galaxies like our Milky Way have flat, rotating disks with elegant spiral arms winding outward from a central bulge. These spiral arms are not fixed structures, but waves of star formation moving through the galactic disk like ripples on a pond. New stars form primarily within these arms, where gas and dust are compressed by the spiral density wave, triggering gravitational collapse into new stellar systems. Elliptical galaxies, by contrast, lack the organized structure of spiral galaxies. They appear as smooth, featureless ellipsoids of stars moving in random orbits around the galactic center. These galaxies contain primarily older stars and little gas or dust, suggesting they have exhausted most of their star-forming material. Many elliptical galaxies are thought to form through mergers of spiral galaxies, cosmic collisions that scramble the ordered motion of stars into the random orbits we observe. Irregular galaxies show no clear structure at all, with stars, gas, and dust distributed chaotically. Many irregular galaxies are small satellites of larger galaxies, their structure disrupted by gravitational interactions with their more massive neighbors. Others may be young galaxies still in the process of forming, or older galaxies disturbed by recent collisions. The shapes and structures of galaxies are not fixed, but evolve over cosmic time. When the universe was young, galaxies were smaller, more numerous, and more irregular than they are today. Over billions of years, galaxies have grown through two primary processes. First, they continue to accrete gas from the intergalactic medium, providing new material for star formation. Second, they merge with other galaxies in cosmic collisions that unfold over hundreds of millions of years. These galactic mergers are among the most dramatic events in cosmic evolution. When two galaxies pass close enough to each other, their mutual gravitational attraction can draw them into a dance that eventually leads to their merger into a single, larger galaxy. During this process, the gravitational forces between the galaxies create tidal tails, long streamers of stars and gas thrown outward from the colliding galaxies. These beautiful structures can stretch for hundreds of thousands of light years, temporary cosmic calligraphy written by gravity across the void. Despite the violence of these collisions on a galactic scale, individual stars rarely collide during galaxy mergers. The distances between stars are so vast compared to their sizes that they generally pass by each other undisturbed, like ships in a very large night. The gas and dust between stars, however, can collide and compress, triggering bursts of star formation that illuminate the merging galaxies with the light of newly born stars. Our own Milky Way galaxy has grown through many such mergers throughout its history. Even now, it is in the process of consuming several smaller satellite galaxies, including the Sagittarius Dwarf elliptical galaxy, which is currently being torn apart by the Milky Way's gravitational field. And in about 4 billion years, the Milky Way will begin a collision with the Andromeda galaxy, our largest galactic neighbor. Over the course of hundreds of millions of years, these two spiral galaxies will merge to form a single elliptical galaxy that astronomers have already named Milkomeda. Galaxy clusters represent the next level of cosmic structure, collections of hundreds or thousands of galaxies bound together by gravity. The Virgo cluster, the nearest large cluster to the Milky Way, contains about 2,000 galaxies. The space between these galaxies is filled with hot gas, heated to tens of millions of degrees Celsius by the gravitational energy released as the cluster formed. This gas is so hot it emits X-rays, making galaxy clusters some of the brightest X-ray sources in the universe. At an even larger scale, galaxy clusters themselves are organized into superclusters, enormous collections of dozens or hundreds of clusters spanning hundreds of millions of light years. The Laniakea supercluster, which includes our local group of galaxies, contains about 100,000 galaxies spread across more than 500 million light years. These superclusters form the nodes of the cosmic web, the largest coherent structures we can observe. The evolution of these structures through time follows a hierarchical pattern, with smaller structures forming first and then merging to create larger ones. In the early universe, the first galaxies were small collections of stars, perhaps similar to the dwarf galaxies that orbit the Milky Way today. These small galaxies then merge to form larger ones, which in turn merge to form the giant galaxies we see in the centers of galaxy clusters. This process of hierarchical structure formation continues today. Gravitational attraction is gradually pulling the components of the cosmic web closer together, causing galaxy clusters to merge into larger clusters and superclusters to become more tightly bound. However, the accelerating expansion of the universe, driven by dark energy, is working against this process, pulling distant regions of the cosmos away from each other at an ever-increasing rate. The tension between gravity's pull and dark energy's push shapes the future evolution of cosmic structure. Computer simulations suggest that in the far future, perhaps 100 billion years from now, each supercluster will become an island universe, completely isolated from other superclusters by the expanding void. Eventually, even the galaxies within these superclusters will merge into enormous elliptical galaxies as star formation ceases and the universe grows increasingly quiet. Having explored the largest scales of cosmic structure, let us now turn our attention to the formation of individual stars and planetary systems, where time crafts the environments that can potentially harbor life. Stars form within galaxies from clouds of gas and dust called molecular clouds. These clouds can be enormous, spanning hundreds of light years and containing enough material to form thousands or millions of stars. Within these clouds, gravity works to pull matter together, but it is opposed by various forms of pressure, including thermal pressure from the temperature of the gas, magnetic pressure from magnetic fields threading through the cloud, and turbulent pressure from the random motions of gas within the cloud. For a star to begin forming, some portion of the cloud must become dense enough for gravity to overcome these opposing pressures. This can happen when the cloud is compressed by external forces, such as the shock wave from a nearby supernova explosion, or the passage of a spiral density wave through a galactic disk. When enough mass is concentrated in a small enough volume, gravity takes over and the region begins to collapse inward. As the collapsing cloud fragment grows denser, it breaks up into smaller fragments, each of which may eventually form a star. This fragmentation process explains why most stars form in clusters rather than in isolation. The Orion Nebula, visible to the naked eye as a fuzzy patch in the constellation Orion, is one such stellar nursery, currently forming thousands of new stars. Each collapsing fragment forms a protostar, a dense concentration of gas that continues to grow as material from the surrounding cloud falls onto it. As the protostar accumulates mass, its core becomes increasingly hot and dense due to the gravitational energy released during collapse. When the temperature and pressure at the core become high enough, nuclear fusion begins, marking the birth of a true star. This process of star formation is not instantaneous but unfolds over millions of years. A typical low-mass star, like our Sun, takes about 10 million years to evolve from a collapsing cloud fragment to a fully formed star. More massive stars evolve more quickly, while less massive stars take longer to form. Across the Milky Way, stars are being born and dying continuously, a cycle of stellar life and death that has continued for more than 13 billion years. Around many of these newborn stars, disks of gas and dust remain, the leftover material from the star formation process. Within these protoplanetary disks, small particles of dust begin to stick together, forming pebbles, then rocks, then larger bodies called planetesimals. This process of accretion continues as planetesimals collide and merge, gradually building planets over tens of millions of years. The young solar system was a chaotic place, with frequent collisions between planetesimals and young planets. Our moon likely formed when a Mars-sized object collided with the early Earth, throwing debris into orbit that eventually coalesced into our lunar companion. Similar impacts may have determined the unusual rotation of Venus, which spins backward compared to most planets, and the extreme tilt of Uranus, which rotates almost on its side. The timescales of planetary formation are difficult to comprehend from our human perspective. The Earth took roughly 100 million years to form, a period more than 500 times longer than our species has existed. The processes that shaped our planet, from the initial accretion of material to the differentiation of the core, mantle and crust, to the formation of the oceans and atmosphere, unfolded over hundreds of millions to billions of years. Even today, these geological processes continue. Continents drift across the face of our planet at rates of a few centimeters per year, roughly the rate at which your fingernails grow. Mountains rise and are worn down by erosion. Volcanoes build new land. Time and geology work together to sculpt the face of our world, just as time and gravity sculpt the larger structures of the cosmos. The discovery of thousands of exoplanets, planets orbiting stars other than our Sun, has revealed that planetary systems are common throughout the galaxy. These systems display remarkable diversity, with architectures often very different from our solar system. Some have massive gas giants orbiting very close to their stars, unlike our solar system, where the gas giants Jupiter and Saturn orbit much farther out. Others have multiple planets packed into orbits tighter than Mercury's path around our Sun. This diversity reminds us that the processes of planet formation are not rigid but flexible, producing a wide range of outcomes depending on the specific conditions in each protoplanetary disk. Time does not follow a single path in shaping planetary systems, but explores many possibilities, creating a cosmic laboratory of worlds with different sizes, compositions, and orbital arrangements. Throughout all these processes, from the formation of the cosmic web to the birth of stars and planets, time is the essential ingredient. Without the billions of years of cosmic evolution, the universe would still be a diffuse fog of hydrogen and helium, without the complex structures we observe today. Time allows gravity to do its work, gathering matter into increasingly complex arrangements against the backdrop of expanding space. Time also allows for the creation of the heavy elements necessary for planets like Earth and life forms like us. When the universe began, it contained only the lightest elements, primarily hydrogen and helium with traces of lithium. All the heavier elements, from carbon and oxygen to iron and uranium, had to be created through nuclear fusion in the hearts of stars or during stellar explosions. This process of stellar nucleosynthesis is time-dependent. Stars fuse hydrogen into helium, then at higher temperatures fuse helium into carbon and oxygen, then at still higher temperatures create elements up to iron. Elements heavier than iron are primarily created during supernova explosions or neutron star mergers, where enormous energies enable nuclear reactions that are impossible under normal stellar conditions. Each generation of stars enriches the interstellar medium with these newly created heavy elements when they die, either gently through planetary nebulae for stars like our Sun, or violently through supernova explosions for more massive stars. This enriched material then becomes part of the next generation of stars and their planetary systems. Our solar system contains material processed through multiple generations of stars, a cosmic recycling program that has operated for billions of years. The abundance of heavy elements has increased over cosmic time, making later generations of planetary systems potentially more hospitable to life as we know it. Earth, and the life it supports, are built from atoms that were forged in ancient stars long before our Sun was born. As the astronomer Carl Sagan famously noted, "We are star stuff, our physical connection to the cosmos written in the very atoms of our bodies." This perspective reveals time not just as a dimension in which events occur, but as a creative force that builds complexity from simplicity, structure from chaos, and eventually consciousness from unconscious matter. Without time, the universe would be static and unchanging. With time, it becomes a story of evolution and emergence, a drama in which new properties and possibilities arise that could not have been predicted from initial conditions alone. In our exploration of cosmic structure, we've seen how time works with gravity to create galaxies, stars, and planets. But time also creates opportunities for the emergence of life. On at least one planet, and perhaps on many others, the chemical elements forged in stars have organized themselves into living systems capable of replication, adaptation, and eventually consciousness. This emergence of life and mind represents another level of structure in the cosmos, one that may be as significant in its own way as the formation of galaxies or stars. Just as gravity organizes matter into large-scale cosmic structures, other forces, including the electromagnetic interactions between atoms and molecules, organize matter into the intricate patterns we call life. Life on Earth has existed for at least 3.5 billion years, most of that time in the form of single-celled organisms. Multicellular life appeared much more recently, perhaps about 600 million years ago, with humans arriving on the scene only in the last few 100,000 years. Yet in our brief existence, we have developed the capacity to comprehend the vast scales of space and time that shaped the universe before us. This capacity for understanding represents a new development in cosmic evolution. Through science and mathematics, human minds can reconstruct the history of the universe, from the Big Bang through the formation of galaxies, stars, and planets, to the emergence of life and consciousness. We can trace our ancestry not just to earlier life forms, but to the stars that created the elements of which we are made, and ultimately, to the primordial hydrogen formed in the first minutes after the Big Bang. Our ability to comprehend cosmic history represents a kind of closing of a circle. The universe, through the patient work of time, has produced beings capable of understanding their own origins. In a sense, the universe has become conscious of itself through us, and potentially through other intelligent life forms elsewhere in the cosmos. This perspective invites us to see ourselves not as separate from cosmic evolution, but as part of it. A recent chapter in an ongoing story that began nearly 14 billion years ago. Our existence is not an accident, but a natural outcome of physical processes operating over enormous spans of time. We are, in a very real sense, the universe becoming aware of itself. As we continue our journey through cosmic time, we carry this awareness with us. We recognize that the structures we observe in the cosmos, from the largest superclusters to the smallest living cells, are all products of time's creative work. Without time, none of this complexity would exist. The universe would be forever frozen in its initial state, without galaxies, stars, planets, or life. Instead, time has allowed the universe to unfold its potential, to explore the possibilities inherent in its physical laws, to create structures of astonishing diversity and beauty, from the elegant spiral arms of galaxies to the intricate biochemistry of living cells. Time has written a cosmic story of ever-increasing complexity and wonder. Given enough time, matter dances into spirals, filaments, and flames. Stars are the timekeepers of the cosmos. Each star follows its own temporal rhythm, a life cycle determined by its mass, burning bright and fast or slow and steady across the vastness of cosmic time. These stellar clocks mark the cadence of universal evolution, creating the elements, illuminating galaxies, and providing the energy that makes life possible. In this chapter, we explore how stars experience time and how their varied lifespans shape the cosmos around us. When we gaze at the night sky, we see stars not as they are now, but as they were when their light began its journey to Earth. The star Sirius, brightest in our night sky, appears to us as it was 8.6 years ago. The light from Betelgeuse in the constellation Orion began its journey about 640 years ago. The stars of the Andromeda Galaxy that we observe tonight sent their light toward us 2.5 million years in the past, when our human ancestors were just beginning to use stone tools. This delay between a star's existence and our perception of it reminds us that looking outward into space is looking backward in time. The universe we observe is always a historical record, never the present moment. The more distant the object, the further back in time we see. This relationship between space and time provides astronomers with a cosmic time machine, allowing them to directly observe earlier epochs in the universe's history by studying very distant objects. But stars are more than passive markers in this cosmic chronology. They are active participants in the flow of time, their internal processes governed by physical laws that dictate how quickly they evolve and how long they live. A star's lifespan is primarily determined by its mass, a relationship that seems counterintuitive at first glance. The most massive stars, those with 15 or more times the mass of our Sun, are the cosmic equivalent of rock stars, living fast, burning bright, and dying young. Despite their enormous fuel reserves, these stellar giants consume their hydrogen at a prodigious rate, their cores reaching temperatures of 40 million degrees Celsius or more. At these extreme temperatures, nuclear fusion proceeds at a furious pace, causing massive stars to shine hundreds of thousands of times brighter than our Sun. This extravagant energy production comes at a cost. A truly massive star with 40 times the Sun's mass will exhaust its nuclear fuel in just a few million years, a mere eye blink in cosmic terms. By comparison, Our Sun is currently about 4.6 billion years into its expected 10 billion year lifespan. These massive stars race through their evolutionary stages, their internal clocks dramatically accelerated by their own gravity. At the other extreme, the smallest stars, red dwarfs with less than half the Sun's mass, burn their fuel with miserly efficiency. Their cores reach temperatures of only about 3 million degrees Celsius, sufficient for nuclear fusion, but at a much slower rate than in more massive stars. The smallest red dwarfs, with about 10% of the Sun's mass, use their fuel so sparingly that they can continue shining for up to 10 trillion years, nearly 1,000 times longer than the current age of the universe. This inverse relationship between stellar mass and lifespan means that every star follows its own temporal path. If stars had consciousness, a massive blue giant would experience time very differently than a small red dwarf. The blue giant would live its entire life in the time it takes the red dwarf to complete just the opening moments of its existence. From the perspective of the longest-lived stars, the massive giants are like mayflies, here and gone in an instant, while from the perspective of the giants, the dwarfs seem nearly frozen in time. Let us follow the life cycle of a star like our Sun to understand how these cosmic clocks tick. Our Sun began its life about 4.6 billion years ago, condensing from a cloud of gas and dust. As gravity pulled this material inward, the increasing pressure raised the temperature at the center of the forming star. When the core temperature reached about 15 million degrees Celsius, hydrogen nuclei began to fuse into helium, releasing the energy that has powered our Sun ever since. This hydrogen fusion occurs through a process called the proton-proton chain. 4 hydrogen nuclei combine to form one helium nucleus, releasing energy in the form of gamma rays and neutrinos. The gamma rays slowly work their way outward from the core, taking between 10,000 and 170,000 years to reach the Sun's surface. There, this energy is radiated into space as the sunlight that illuminates our world. Our Sun will continue fusing hydrogen in its core for another 5 billion years or so. During this main sequence phase, the Sun remains relatively stable, gradually increasing in brightness by about 10% every billion years. This slow brightening has significant consequences for Earth and may eventually make our planet too warm for liquid water to exist on its surface, long before the Sun leaves the main sequence. When the hydrogen in the Sun's core is eventually exhausted, dramatic changes will begin. With no fusion occurring in the core, gravity will cause it to contract and heat up. Meanwhile, a shell of hydrogen fusion will ignite around this inert helium core, generating more energy than before and causing the Sun's outer layers to expand dramatically. The Sun will become a red giant, swelling to hundreds of times its current size, possibly engulfing the orbits of Mercury and Venus, and perhaps reaching as far as Earth. As the helium core continues to contract and heat, it will eventually reach a temperature of about 100 million degrees Celsius. At this point, helium nuclei will begin to fuse into carbon in a process called the triple alpha reaction. This helium fusion begins explosively in lower mass stars like our Sun, an event called the helium flash, and then continues more stably for a period of about 100 million years. When the helium in the core is exhausted, the Sun will not be massive enough to reach the temperatures needed to fuse carbon into heavier elements. Instead, it will enter a brief phase of instability, with helium fusion occurring in a shell around the carbon core and hydrogen fusion continuing in a shell further out. During this phase, the Sun will shed its outer layers, forming an expanding shell of gas called a planetary nebula. The core that remains will be a white dwarf, a dense remnant about the size of Earth, but containing nearly 60% of the Sun's original mass. This white dwarf will be extraordinarily hot at first, with a surface temperature of about 100,000 degrees Celsius, but with no fusion occurring, it will have no way to generate new energy. Over the next several billion years, the white dwarf will gradually cool, eventually becoming a cold, dark black dwarf. This fate, to end as a cooling cinder, awaits all stars with less than about 8 times the mass of our Sun. But more massive stars follow a different path, one that leads to some of the most dramatic events in the cosmos. In stars with more than 8 solar masses, the temperatures and pressures after helium fusion are high enough to ignite carbon fusion, creating neon and magnesium. As these stars continue to evolve, they develop an onion-like structure, with concentric shells of different elements undergoing fusion at different temperatures. The most massive stars can create elements up to iron through this process of nuclear fusion. Iron represents a turning point in stellar evolution. Fusing lighter elements into iron releases energy, but fusing iron into heavier elements requires an input of energy. When a massive star develops an iron core, it reaches a crisis point. With no way to generate energy from the core to counteract gravity, catastrophic collapse becomes inevitable. This collapse occurs with stunning rapidity. In less than a second, the star's core shrinks from about 8,000 kilometers in diameter to just a few tens of kilometers. The outer layers of the star fall inward, then rebound off the newly formed dense neutron core, creating a shockwave that races outward. This shock, combined with a flood of neutrinos from the collapsed core, tears the star apart in a supernova explosion. A supernova can briefly outshine an entire galaxy, releasing as much energy in a few weeks as our Sun will produce in its entire 10 billion year lifetime. During this explosion, temperatures and pressures become high enough to create all the elements heavier than iron, from copper and zinc to gold and uranium. These newly formed elements, along with those created earlier in the star's life, are scattered into space by the explosion, enriching the interstellar medium from which future stars and planets will form. What remains after a supernova depends on the original mass of the star. Stars between about 8 and 20 solar masses leave behind a neutron star, an object so dense that a teaspoonful of its material would weigh about 1 billion tons on Earth. These neutron stars often spin rapidly, with some rotating hundreds of times per second. As they spin, they emit beams of radiation from their magnetic poles, which sweep across space like cosmic lighthouses. If one of these beams crosses Earth, we detect a regular pulse of radiation, giving these objects their alternative name, pulsars. For stars with more than about 20 solar masses, not even the pressure of neutrons can halt the collapse. These stars leave behind black holes, objects so dense that not even light can escape their gravitational pull. At the center of a black hole lies a singularity, a point where, according to our current theories, space and time themselves break down. Around this singularity is the event horizon, a boundary beyond which nothing can return to the normal universe. Black holes represent the most extreme warping of space-time known to physics. Near a black hole, time itself behaves strangely. From the perspective of a distant observer, a clock falling toward a black hole would appear to tick more and more slowly, eventually freezing at the event horizon. But from the perspective of someone falling with the clock, time would continue to pass normally as they crossed the event horizon, though they would be unable to communicate this experience to the outside universe. This time dilation near black holes is not merely theoretical. The black hole at the center of our galaxy, Sagittarius A star, has a mass of about 4 million times that of our Sun. Time passes more slowly in the intense gravitational field near this object, a fact that astronomers must account for when studying the orbits of stars in the galactic center. While black holes and neutron stars represent the endpoints for massive stars, let us return to the broader patterns of stellar evolution across cosmic time. The very first stars in the universe, called population 3 stars, formed about 200 million years after the Big Bang. These stars contained only the primordial elements hydrogen, helium, and traces of lithium, with essentially no heavier elements. Without heavier elements to help radiate away heat during collapse, these first stars grew to enormous sizes, perhaps 100 or more times the mass of our Sun. They were extremely hot and bright, living for only a few million years before exploding as supernovae. These explosions created the first heavy elements beyond those formed in the Big Bang, beginning the process of cosmic chemical enrichment. The next generation of stars, population 2, formed from material containing small amounts of these newly created heavy elements. These stars are found primarily in the halos and globular clusters of galaxies, regions that formed early in galactic history. They have low metallicity, the astronomical term for the abundance of elements heavier than helium, typically less than 1/10 that of our Sun. Population 1 stars like our Sun formed much more recently, from interstellar material that had been enriched by multiple generations of previous stars. These stars have higher metallicity and are found primarily in the disks of spiral galaxies, regions of ongoing star formation. Our Sun, despite being more than 4 billion years old, is relatively young in cosmic terms, part of a stellar generation that could not have existed in the early universe before sufficient heavy elements had been created. This classification of stellar populations tells a story of cosmic chemical evolution through time. The universe began with only the lightest elements and has progressively created heavier elements through stellar nucleosynthesis. Each generation of stars leaves the universe more chemically diverse than it found it, a process that continues today in the spiral arms of galaxies throughout the cosmos. The rate of star formation has not been constant over cosmic history. The universe experienced a peak of star formation between about 8 and 11 billion years ago, a period sometimes called cosmic noon. During this era, the average star formation rate in the universe was about 10 times higher than it is today. Since then, the rate has steadily declined as the supply of gas for forming new stars has diminished. This decline in star formation represents a kind of cosmic autumn. The universe's most prolific period of stellar birth is behind us, and in the distant future, star formation will become increasingly rare. Trillions of years from now, when the last gas clouds have either formed stars or been ejected from galaxies, the era of starbirth will end. From that point forward, the stellar population of the universe will consist only of those stars already formed, gradually winking out as they reach the ends of their lifespans. The longest-lived stars, the smallest red dwarfs, will continue shining for up to 10 trillion years, but eventually, even they will exhaust their hydrogen fuel. In the far distant future, perhaps 100 trillion years from now, the last stars will fade to darkness, and the universe will enter a new phase, dominated by stellar remnants, black holes, neutron stars, and white dwarfs. Before we reach that distant future, the stellar clocks currently ticking throughout the cosmos continue to shape galactic evolution. When massive stars explode as supernovae, they inject energy into the surrounding interstellar medium, compressing nearby gas clouds and potentially triggering new episodes of star formation. These stellar feedback processes can both promote and inhibit star formation, creating a complex regulatory system that influences the overall star formation rate in a galaxy. Supernovae and stellar winds from massive stars also chemically enrich the interstellar medium, gradually increasing the abundance of heavy elements available for forming new stars and planets. This enrichment has important implications for the formation of habitable worlds. The heavy elements created by stars, particularly carbon, oxygen, nitrogen, phosphorus, and sulfur, are essential building blocks for planets like Earth and for life as we know it. The connection between stellar lifespans and the possibility of life is profound. If stars lived significantly shorter lives, there might not be enough time for complex life to evolve on their planets before the stars died. If all stars lived as long as the smallest red dwarfs, the universe would be very different, with much less chemical enrichment and potentially fewer habitable planets. Our Sun represents a fortuitous middle ground, massive enough to produce significant energy and create a habitable zone where liquid water can exist on Earth's surface, yet small enough to remain stable for billions of years, providing the time needed for complex life to evolve. This balance between energy output and longevity makes stars like our Sun particularly important in discussions of habitability throughout the galaxy. As we contemplate the varied lifespans of stars, from the brief, brilliant lives of blue giants to the almost unimaginably long existences of red dwarfs, we gain perspective on our own place in cosmic time. Our Sun is currently about halfway through its main sequence lifetime, providing Earth with a relatively stable environment for billions of years. This stability has allowed life to evolve from single-celled organisms to the complex biosphere we see today, including creatures capable of contemplating the stars themselves. Yet even this apparently stable environment changes over time. The Sun has grown about 30% brighter since its birth 4.6 billion years ago, a gradual increase that has been partially offset on Earth by changes in atmospheric composition. In another billion years or so, the Sun will become bright enough that Earth may lose its oceans to evaporation, ending the reign of complex life on our planet long before the Sun itself leaves the main sequence. This reminder of impermanence puts our human existence into cosmic perspective. We live in a window of habitability that will not last forever, on a planet orbiting a star of finite lifespan, in a universe where everything changes given enough time. Our brief moment of consciousness exists within these nested timeframes, our human story a paragraph in the longer story of Earth, which is itself a chapter in the epic of stellar evolution. Yet within this brief moment, we have developed the capacity to understand the stars, to measure their lifespans, to trace their evolutionary paths, and to recognize our own origins in their fiery hearts. The atoms that form our bodies were created in stars that lived and died before our sun was born. We are, in a very real sense, children of the stars, connected to cosmic time through the elements of which we are made. Every star carries its own timeline, its own story, its own end. Time flows differently through human awareness than it does through the cosmos. While stars measure their lives in millions or billions of years, we experience time in heartbeats, in breaths, in moments of joy and sorrow that can seem both fleeting and eternal. Our perception of time exists at the intersection of physics and consciousness, shaped by evolution, biology, memory, and emotion. In this chapter, we explore the subjective dimension of time, the ways we experience, measure, and remember its passage. The human brain is exquisitely sensitive to time. We can distinguish events separated by as little as 5 milliseconds, a capability essential for locating sounds in space. We can synchronize our movements to precise rhythms, allowing us to create and enjoy music across cultures. We can anticipate future events, plan complex sequences of actions, and mentally travel through time, revisiting the past and imagining the future. Yet, despite this temporal sensitivity, our perception of time's passage is remarkably fluid. A minute spent in pain seems to stretch endlessly, while an hour engaged in something deeply enjoyable can vanish in what feels like moments. Time appears to speed up as we age, with years seeming to pass more quickly in later life than they did in childhood. During emergencies, time can seem to slow dramatically, allowing for the impression of deliberate thought and action in fractions of a second. These variations in subjective time reveal that our experience is not simply a faithful recording of physical time. Instead, our brains actively construct our sense of duration and succession, integrating information from multiple sources to create our temporal reality. This constructed nature of time perception becomes particularly evident when the system falters, as it can in certain neurological conditions, during meditation, or under the influence of psychoactive substances. Our perception of time operates across multiple scales, from the microsecond timing required for sound localization to the decades spanned by autobiographical memory. These different temporal scales are processed by different neural systems, creating a layered architecture of time in the human brain. At the shortest timescales, from milliseconds to seconds, timing relies primarily on neural circuits in the cerebellum and basal ganglia. These systems operate largely automatically, below the level of conscious awareness, enabling precise timing for movement, speech, and auditory processing. A musician's ability to maintain a steady rhythm or a dancer's capacity to move in precise synchrony with music depends on these rapid, unconscious timing mechanisms. At intermediate timescales, from seconds to minutes, the brain's timing systems become more distributed, involving the prefrontal cortex, parietal cortex, and insular cortex. These regions integrate sensory information, attention, and memory to create our conscious experience of duration. This is the level at which we notice time passing, feel boredom or engagement, and make judgments about how long activities have lasted or will take. At the longest timescales, from days to years, our sense of time depends primarily on memory systems centered in the hippocampus and surrounding structures. These systems organize our experiences into coherent episodes and autobiographical narratives that give structure to our past and allow us to imagine possible futures. Our sense of life's passage, of seasons and years flowing one into another, emerges from these memory systems rather than from direct perception. The flexibility of human time perception likely evolved because it offers significant adaptive advantages. Time seems to slow during dangerous situations because more neural resources are devoted to processing sensory information, creating more detailed memories that make the event seem to have lasted longer in retrospect. This heightened processing can help us respond more effectively to threats, even if it doesn't actually slow physical time. Similarly, Our tendency to pay less attention to routine or predictable experiences means they occupy less space in memory, making familiar periods seem to have passed more quickly than novel ones. This efficiency allows us to devote more cognitive resources to new or changing aspects of our environment, where attention is most valuable for survival and learning. The perception that time speeds up with age may result from several factors. As we grow older, each new duration represents a smaller fraction of our total lifespan, potentially making it seem proportionally shorter. Additionally, childhood is filled with novel experiences that create dense, detailed memories, while adult life often involves more routine and familiarity, resulting in fewer distinct memory markers. When we look back, periods with fewer memorable events seem to have passed more quickly. Our experience of time is also shaped by our emotional states. Fear and anxiety can dramatically slow subjective time, an effect that may have evolved to give us more time to respond to threats. Positive emotions have more variable effects, sometimes speeding time when we're engaged in enjoyable activities, a state psychologists call flow, and sometimes slowing it during moments of peak pleasure, allowing us to savor positive experiences. The flow state represents a particularly interesting aspect of time perception. When we are completely immersed in a challenging but manageable activity, self-consciousness falls away and time seems to transform. Hours can pass in what feels like minutes, and yet the experience often includes a paradoxical sense of expanded time, where complex actions unfold with a feeling of effortless clarity. Musicians, athletes, writers, and others who regularly experience flow often describe it as a temporary stepping outside of normal time constraints. Depression and boredom have the opposite effect, stretching time painfully. Minutes can feel like hours when we are disengaged, unstimulated, or experiencing psychological distress. This slowing of subjective time during negative states may explain why witnessing a clock's movement when waiting for something to end can seem almost surreal, with seconds appearing to take much longer than they should. Our experience of time is intimately connected to attention. When we focus intensely on the passage of time itself, it typically seems to slow. Conversely, when our attention is captured by engaging activities, we often lose track of time completely. This relationship between attention and temporal experience helps explain why boredom stretches time while flow compresses it. Memory plays an equally crucial role in our perception of time. Our experience of duration depends not only on the period as we live through it, but also on how we remember it afterward. Dense, detailed memories make experiences seem to have lasted longer in retrospect, while periods that left few distinct memory traces seem to have passed quickly. This creates a fascinating paradox. Engaging activities that seem to pass quickly in the moment often expand in retrospect because they create rich memories, while boring periods that seem endless as we endure them may shrink in memory because they left little trace. The psychologist Daniel Kahneman has distinguished between the experiencing self that lives through moments sequentially and the remembering self that constructs the narrative of our lives. These two selves can have dramatically different perceptions of the same temporal experience. A vacation might include many hours of tedious travel that the experiencing self finds unpleasant and lengthy. But if the destination provides intensely positive moments, the remembering self might recall the entire experience as wonderful and too brief. Our biological rhythms provide another foundation for our experience of time. The circadian clock, centered in the suprachiasmatic nucleus of the hypothalamus, regulates a roughly 24-hour cycle of physiological processes, including sleep-wake patterns, hormone release, body temperature, and cognitive function. This internal timekeeper synchronizes with environmental cues, primarily daylight, to align our biology with the planet's rotation. Beyond the daily circadian rhythm, our bodies maintain numerous other cycles operating at different timescales. Ultradian rhythms govern fluctuations in alertness and cognitive performance across 90 to 120-minute cycles throughout the day. Infradian rhythms regulate longer processes, such as menstrual cycles or seasonal changes in mood and behavior. These nested biological rhythms create a temporal architecture for our lives, a bodily calendar and clock that operates largely beneath conscious awareness. Disruptions to these biological rhythms can profoundly affect our experience of time and overall well-being. Jet lag, shift work, and seasonal changes in daylight can desynchronize our internal clocks, leading to disorientation, fatigue, mood disturbances, and a sense that time itself has become somehow wrong or untrustworthy. The modern world, with its artificial lighting, global travel, and around-the-clock connectivity, creates unprecedented challenges for our evolutionarily ancient timing systems. Cultural differences in time perception reveal that our experience is shaped not only by biology and psychology, but also by shared beliefs and practices. Western industrialized societies typically emphasize linear, clock-measured time, with a focus on punctuality, efficiency, and scheduling. Many traditional societies, by contrast, orient more toward event-based time, where activities take as long as they naturally require and are coordinated based on completion of previous activities rather than arbitrary clock time. Some languages encode different relationships to time in their very structure. English and many other languages treat time as a spatial dimension along which we move or which moves past us, with the future ahead and the past behind. But the Aymara language of South America reverses this mapping, placing the future behind, unseen, and the past ahead, visible. The Hopi language, according to some analyses, structures time based on manifestation rather than linear progression, distinguishing between manifest, present and past, and manifesting, future, rather than past, present and future. These cultural and linguistic differences remind us that our experience of time is not simply given by physics, but is actively constructed through shared conceptual frameworks. How we think and talk about time shapes how we experience it, creating feedback between culture, cognition, and perception. The relationship between human time perception and physical time raises profound philosophical questions. Einstein's theories of relativity demonstrated that physical time is not absolute, but relative to the observer's frame of reference. Psychological research shows that subjective time is even more relative, shaped by attention, emotion, memory, and expectation. These two forms of relativity, physical and psychological, suggest that time as we experience it emerges from the interaction between mind and world, rather than existing independently of observation. Some philosophers, following Immanuel Kant, argue that time is not a property of reality itself, but a form of intuition, a lens through which conscious beings experience the world. Others maintain that time exists independently of perception, but acknowledge that our experience captures only certain aspects of this objective temporal reality. The relationship between physical and psychological time remains an open question at the intersection of physics, neuroscience, and philosophy. This philosophical ambiguity becomes particularly evident when we consider the present moment, the now that seems so central to human experience. Physics offers no special status to the present, describing space-time as a four-dimensional block where past, present, and future exist on equal footing. Yet our subjective experience insists on the specialness of now, the moving spotlight of consciousness that illuminates one moment after another. Neuroscience suggests that this experience of now is a construction of the brain, integrating sensory information that arrives at different speeds into a seemingly unified present moment. What we experience as now actually spans about 100 milliseconds of physical time, a duration that allows the brain to synchronize information from different sensory modalities despite their different processing speeds. Visual information, for instance, takes longer to process than auditory information, but the brain adjusts for this difference to create the impression of simultaneous sight and sound. This constructed nature of the present becomes apparent in certain illusions, where the brain reorganizes the perceived order of events to maintain causal coherence. In the cutaneous rabbit illusion, for example, a series of rapid taps on the wrist and then the elbow creates the feeling of taps hopping up the arm in between these points. Even though no physical stimulation occurred there, the brain retroactively constructs this experience after receiving the elbow tap, essentially reaching backward in subjective time to create a coherent motion narrative. The arrow of time, the directional flow from past to future that seems so fundamental to our experience, presents another fascinating intersection between physics and perception. In most physical laws, time is reversible, with no fundamental distinction between past and future directions. A film of two billiard balls colliding would look equally valid played forward or backward. Yet we never observe broken cups reassembling themselves, or heat flowing from cold objects to warm ones. This one-way flow in macroscopic phenomena results from the second law of thermodynamics, which states that the total entropy of an isolated system always increases over time. But why should entropy increase in one temporal direction rather than the other? Some physicists suggest that the arrow of time ultimately stems from the low entropy initial conditions of the universe after the Big Bang, creating a cosmic asymmetry that propagates through all physical processes. Our psychological experience of time's arrow may be intimately connected to this thermodynamic asymmetry. Memory, which allows us to recall the past but not the future, depends on creating enduring physical records, a process that increases entropy. Perhaps consciousness itself, with its apparent flow from past to future, emerges from the same entropic processes that give time its macroscopic direction. The human capacity for mental time travel, our ability to revisit the past and imagine the future in conscious thought, represents one of our most distinctive cognitive abilities. Using episodic memory, we can mentally transport ourselves to previous experiences, reliving them with something of their original sensory and emotional quality. Using this same system, we can project ourselves into hypothetical futures, simulating potential experiences before they occur. This capacity for mental time travel appears to be uniquely human, at least in its fully developed form. While other animals show various forms of memory and anticipation, the ability to consciously revisit specific past experiences and imagine detailed future scenarios may be a human specialization. This cognitive time machine gives us tremendous adaptive advantages, allowing us to learn from past experiences, plan for future contingencies, and make decisions based on simulated outcomes rather than trial and error. The neural basis for mental time travel involves a network of brain regions, including the hippocampus, prefrontal cortex, and posterior parietal cortex. Interestingly, similar areas activate whether we are remembering the past or imagining the future, suggesting that these apparently opposite temporal directions rely on shared cognitive machinery. We construct possible futures using building blocks from remembered pasts, reshuffled and recombined to create novel scenarios. This constructive nature of memory and imagination means that neither our recalled past nor our anticipated future precisely reflects reality. Memory is not a perfect recording, but an active reconstruction influenced by our current knowledge, beliefs, and emotional state. Similarly, our imagined futures often fail to account for factors that will actually influence our experiences, leading to systematic errors in predicting how future events will affect us. Our subjective timeline stretching from past through present to future is less a reflection of objective reality than a useful fiction constructed by our brains. Despite its imperfections, this subjective timeline provides the narrative continuity that defines our sense of self across time. We experience ourselves as beings with a past and a future, connected through a continuous thread of consciousness, despite changes in our physical bodies, beliefs, preferences, and circumstances. This temporal dimension of selfhood, our sense of being the same person across time despite constant change, represents another way in which time and consciousness are inextricably linked. Alterations in consciousness often involve corresponding alterations in time perception. In dreams, time can flow at variable rates, with what seems like hours of dream experience fitting into minutes of physical time. Similarly, certain meditative states can produce a sense of timelessness or eternal present, temporarily suspending the usual flow of subjective duration. Mystical experiences across cultures and traditions frequently include reports of stepping outside ordinary time, experiencing either a compressed eternity where all time exists at once, or a timeless void where temporal concepts lose meaning entirely. These altered states remind us that our ordinary experience of time, while useful for navigating physical reality, represents just one possible configuration of consciousness. Our perception of time is not fixed, but remarkably plastic, capable of dramatic transformation under different conditions. Perhaps this plasticity offers a glimpse of how consciousness might relate to time beyond the constraints of human neurobiology, in other forms of sentience or other states of being. As we conclude this exploration of time and human perception, we find ourselves returning to the tension between physical and psychological time. Physics describes a universe where time may be relative, but is woven into the very fabric of space-time, a dimension as real as length, width, and height. Yet our lived experience suggests something more fluid and constructed, a subjective dimension shaped by attention, emotion, memory, and meaning. Perhaps this tension dissolves when we recognize that physical and psychological time are not competitors, but complementary aspects of a multifaceted reality. Physical time provides the substrate upon which consciousness unfolds, while psychological time gives meaning and structure to conscious experience. Neither alone captures the full richness of temporal reality, which exists at the intersection of objective patterns and subjective experience. In this meeting of physics and phenomenology, we glimpse something essential about the human condition. We are creatures of time in both its physical and psychological dimensions, simultaneously bound by and creators of temporality. We measure time with clocks and calendars, yet we also transform it through attention and memory. We move through time from birth to death, yet we also move time through us in the stream of conscious experience. We do not just move through time, we feel it, we remember it, we carry it. Time, that seemingly universal heartbeat of existence, holds a profound secret. It does not tick at the same rate everywhere. The flow of time that we experience in our daily lives, the steady rhythm we measure with clocks and calendars, is merely a local phenomenon, tied to our particular location in the cosmos and our state of motion. This revelation, one of the most counterintuitive discoveries in the history of physics, tells us that time is not absolute but relative, flowing at different rates for different observers depending on their circumstances. In the early 20th century, a young patent clerk named Albert Einstein fundamentally transformed our understanding of time. His theories of relativity revealed that time is flexible, stretching and compressing in response to motion and gravity. This flexibility of time is not merely theoretical, but has been confirmed by numerous experiments and is even accounted for in technologies we rely on daily, such as the global positioning system that guides our travels. To understand time dilation, we must first set aside our intuitive sense that time flows universally and embrace a more subtle reality. There are two primary forms of time dilation in Einstein's theories, one arising from relative motion between observers, described by special relativity, and the other resulting from differences in gravitational fields, described by general relativity. Both effects are real, measurable, and have profound implications for our understanding of the cosmos. Let us begin with the time dilation of special relativity, which occurs when two observers are moving relative to each other. Imagine two friends, Elena and Miguel. Elena remains on Earth while Miguel travels in a spaceship at a significant fraction of the speed of light. According to special relativity, Elena will observe Miguel's clock running slower than her own. From her perspective, time within the moving spaceship passes more slowly than time on Earth. This effect becomes noticeable only at velocities approaching the speed of light. If Miguel's ship were traveling at 90% of light speed, Elena would observe that Miguel's clock runs at about 44% of the rate of her own. For every 100 seconds that pass on Earth, Elena would observe only 44 seconds passing for Miguel. Remarkably, from Miguel's perspective aboard the spaceship, it is Elena's clock that appears to run slowly. In his reference frame, he is stationary while Elena and the Earth are moving rapidly past him, and thus he observes time dilation affecting Elena rather than himself. This reciprocal nature of time dilation might seem paradoxical, but it arises from the fact that there is no absolute reference frame in the universe, no cosmic yardstick against which we can measure who is truly moving and who is truly stationary. The apparent paradox resolves when we recognize that Elena and Miguel each observe the other's clock through the filter of light signals that must travel between them, and these signals themselves are affected by their relative motion. Neither observer's perspective is more correct than the other's. Their differing experiences of time are equally valid descriptions of reality from their respective reference frames. This relative time dilation has been confirmed in numerous experiments. In one famous demonstration, scientists placed extremely precise atomic clocks aboard commercial airliners and flew them around the world, later comparing them to identical clocks that remained stationary on Earth. The flying clocks recorded slightly less elapsed time than their Earthbound counterparts, exactly as Einstein's theory predicted. even though the airplanes traveled at only a tiny fraction of the speed of light. Even more dramatic confirmation comes from particle accelerators, where subatomic particles are accelerated to speeds exceeding 99% of light speed. These particles decay at measurably slower rates than identical particles at rest, living much longer from our perspective due to time dilation. A muon, for instance, typically decays in about 2 microseconds when at rest, but when accelerated to near light speed, it can survive for dozens of microseconds in the laboratory reference frame, an elegant demonstration of time's flexibility. The time dilation of special relativity leads to the famous twin paradox thought experiment. Imagine that Elena and Miguel are twins. Miguel embarks on a journey to a distant star system at near light speed, while Elena remains on Earth. After reaching his destination, Miguel returns to Earth, also at near light speed. Upon reunion, the twins discover that Miguel has aged much less than Elena. Miguel might have experienced only a few years passing during his journey, while decades have passed for Elena on Earth. This outcome might seem to contradict the reciprocal nature of time dilation described earlier, where each observer sees the other's clock running slowly. The resolution lies in recognizing that Miguel, unlike Elena, does not remain in a single inertial reference frame throughout the scenario. He must accelerate to begin his journey, decelerate and accelerate again at the turnaround point, and finally decelerate upon returning to Earth. These accelerations break the symmetry between the twins' reference frames, resulting in the very real age difference they experience. The twin paradox is not merely a theoretical curiosity, but describes actual physics that would occur in a sufficiently high-speed journey. If humans ever travel at relativistic speeds to other star systems, time dilation will ensure that more time passes on Earth than is experienced by the travelers. The voyagers would return to an Earth that has aged more than they have, perhaps finding that children they left behind have become older than themselves, a temporal displacement with profound emotional and social implications. The second form of time dilation arises not from motion, but from gravity, as described by Einstein's general theory of relativity. General relativity reveals that gravity is not a force in the conventional sense, but a manifestation of the curvature of space-time. Massive objects, like planets, stars, and black holes, create depressions in the fabric of space-time, and this curvature affects not only the paths of objects moving through space, but also the flow of time itself. In the presence of a gravitational field, time passes more slowly near a massive object than it does farther away. A clock placed on the surface of Earth will tick slightly slower than an identical clock positioned aboard a satellite in orbit. This gravitational time dilation means that time flows more quickly on the top floor of a skyscraper than it does on the ground floor, though the difference is far too small for human perception. While imperceptible in ordinary life, these tiny differences in the flow of time become critical for technologies that require precise timing. The global positioning system, which allows our phones and navigation devices to determine their location with remarkable accuracy, must account for both special and general relativistic time dilation. The atomic clocks aboard GPS satellites run about 45 microseconds faster per day than identical clocks on Earth's surface due to their position in a weaker gravitational field, and about 7 microseconds slower per day due to their orbital velocity, for a net gain of about 38 microseconds daily. These small discrepancies, if not accounted for, would cause GPS position calculations to accumulate errors of about 10 kilometers per day, rendering the system useless for navigation. Engineers precisely adjust the clock frequencies on GPS satellites to compensate for relativistic effects, allowing the system to provide accurate positioning. Each time you use GPS navigation, you are benefiting from practical applications of Einstein's theories of relativity and the reality of time dilation. The gravitational time dilation predicted by general relativity has been confirmed with extraordinary precision through various experiments. In one landmark test, physicists at the National Institute of Standards and Technology placed an aluminum-ion optical clock on an elevator and raised it by just 1 foot, measuring the resulting change in the flow of time. They detected a shift in the clock's rate of about 1 part in 10 to the 16th power, exactly as predicted by general relativity, demonstrating that time truly does flow differently at different heights in a gravitational field. The most extreme gravitational time dilation occurs near black holes, objects so massive and compact that not even light can escape their gravitational pull beyond a boundary called the event horizon. As one approaches a black hole, time dilation becomes increasingly pronounced. An observer watching from a safe distance would see a clock falling towards a black hole tick ever more slowly as it approached the event horizon. From the distant observer's perspective, the clock would appear to freeze completely at the event horizon, never quite crossing this boundary. The light from the clock, struggling to escape the intense gravitational field, would be increasingly redshifted, eventually becoming too faint to detect. To the distant observer, it would seem as though time stops at the event horizon of a black hole. Yet, from the perspective of someone falling with the clock, time would continue to flow normally. They would cross the event horizon without experiencing anything unusual in their local flow of time, though they would notice the universe outside the black hole appearing to evolve at an accelerated rate. Once past the event horizon, they could never communicate their experience to the external universe, as no signal can escape from within this boundary. This extreme time dilation near black holes is not merely theoretical. Astronomers have observed its effects by studying the light emitted by matter swirling around supermassive black holes at the centers of galaxies. The radiation from this infalling material shows precisely the redshift patterns predicted by general relativity, confirming that time truly does slow dramatically in the intense gravitational fields near these cosmic leviathans. The combination of special and general relativistic time dilation creates a complex temporal landscape across the cosmos. Time flows at different rates depending on both location and motion, creating a tapestry of temporal flows rather than a universal tick. On Earth, these variations are tiny, but across the vast scales of the universe, they become profound, with time potentially passing at radically different rates in different regions of the cosmos. Consider, for instance, the time experienced by photons, particles of light that travel at the universal speed limit, 300 million meters per second. According to special relativity, time does not pass at all for a photon. From the perspective of a particle of light, its emission and absorption occur simultaneously, even if they are separated by billions of light years from our perspective. The billions of years that a photon might take to cross intergalactic space represent zero time from the photon's own frame of reference, a concept that stretches the boundaries of human imagination. Similarly, in the most intense gravitational fields of the universe, such as near the singularities at the centers of black holes, general relativity suggests that time and space themselves break down, reaching a limit of our current physical theories. What happens to time in these extreme conditions remains one of the great unsolved problems of theoretical physics, requiring a quantum theory of gravity that has thus far eluded scientists. The malleability of time revealed by relativity has profound philosophical implications. If time flows at different rates for different observers, with no perspective more privileged than any other, then the notion of absolute simultaneity, the idea that events can be universally ordered into past, present, and future, breaks down. Events that appear simultaneous to one observer may occur in different temporal orders for other observers in relative motion, suggesting that our intuitive notions of temporal sequence may be merely artifacts of our particular perspective, rather than fundamental aspects of reality. Some physicists and philosophers, following Einstein's own views, have suggested that the past, present, and future might exist equally in a four-dimensional block universe, with our subjective experience of flowing time being merely the result of our consciousness moving along the time dimension. In this view, sometimes called eternalism, all moments in time exist simultaneously, and the apparent flow of time from past to future is an illusion created by our limited perspective, much as the apparent rotation of the stars around the Earth each night is an illusion created by our planet's rotation. Others maintain that the flow of time is real and fundamental, not merely a psychological construct. They argue that the universe evolves through a sequence of nows, with the future genuinely open and undetermined until it becomes the present. In this view, called presentism, only the present moment truly exists, with the past gone forever and the future yet to be realized. Reconciling this intuitive sense of flowing time with the relativity of simultaneity revealed by Einstein's theories remains a challenge for philosophers of time. Beyond these philosophical questions, the reality of time dilation has practical implications for potential future human activities. If we ever develop spacecraft capable of approaching the speed of light, time dilation would become a central consideration in interstellar travel. A journey to a star system 100 light-years away, traveling at 99% of light speed, would take about 101 years as measured on Earth. But for the travelers aboard the spacecraft, only about 14 years would pass due to time dilation. This relativistic effect could potentially make interstellar exploration feasible within a human lifetime for the travelers, though they would return to an Earth where everyone they knew had lived and died long ago. Time dilation thus offers a form of one-way time travel into the future, allowing travelers to experience future eras that they would not naturally live to see, though at the cost of leaving their own era permanently behind. Time dilation would similarly affect communication between planets or star systems with significant relative velocities. Interstellar messages would need to account for the different rates of time flow experienced by sender and receiver, potentially complicating the establishment of coherent dialogues between civilizations moving at different speeds or located in different gravitational environments. While such scenarios remain speculative given our current technology, they highlight the very real consequences of time's relativity for potential future human expansion into the cosmos. They also remind us that what we experience as the uniform flow of time is merely a local approximation, valid only for observers moving slowly relative to one another and experiencing similar gravitational fields. On Earth, we observe variation in time's flow primarily through precise instruments rather than direct perception. But across the vast distances and extreme conditions of the universe, time's flexibility becomes a dominant factor, shaping the evolution of cosmic structures and the potential paths of life and intelligence. The stars we see in the night sky, for instance, have experienced less time passing than we have since their light began its journey to Earth, due to both their motion relative to us and the gravitational fields they inhabit. The youngest stars, forming now in nebulae like the Orion Nebula, experience time differently than ancient globular clusters orbiting in the halo of our galaxy. Even our Sun's core, where greater pressure creates stronger gravity, experiences time flowing measurably slower than its outer layers, though the difference amounts to only a few microseconds per year. These varied temporal flows throughout the cosmos create a tapestry of time, a universe where each location and state of motion carries its own temporal signature. Far from the simple universal tick we intuitively imagine, time reveals itself through relativity to be a subtle and textured dimension, as rich in variation as the spatial dimensions that shape the physical world. Perhaps the most profound implication of time dilation is the light it sheds on the nature of time itself. Before Einstein, time was generally conceived as an absolute background against which events unfolded, a cosmic metronome ticking at the same rate everywhere. Relativity revealed this conception to be limited, showing time to be an integral part of the physical universe as malleable and responsive to conditions as space itself. In Einstein's unified concept of space-time, time and space are no longer separate entities, but aspects of a single four-dimensional continuum. The flexibility of time revealed by relativity is not a curious anomaly, but a fundamental characteristic of this unified space-time, as essential to the fabric of reality as the three spatial dimensions we more readily perceive. This integration of time into the physical world represents one of the most profound conceptual shifts in the history of science, transforming time from an abstract background parameter into a dynamic physical dimension. Time's flow is not imposed on the universe from outside, but emerges from within it, shaped by the same physical laws that govern matter and energy. The varied rates of time's flow throughout the cosmos remind us that what seems most universal and unchanging in our experience, the steady beat of passing moments, is in fact particular and contingent, a local manifestation of a far more complex reality. Our intuitive sense of time as absolute and uniform served us well for most of human history, allowing us to coordinate activities and navigate our immediate environment. But as our understanding has expanded to encompass the vast scales and extreme conditions of the universe, our conception of time has necessarily evolved, revealing a deeper and more subtle reality. In our daily lives, we rarely notice time's flexibility. The differences in time's flow between the top and bottom of a building, or between a moving vehicle and a stationary observer, are far too small for human perception. But these tiny effects, magnified across astronomical distances or at velocities approaching the speed of light, reshape our understanding of the cosmos and our place within it. Time dilation reminds us that perspective matters fundamentally in how we experience and understand the universe. Different observers in different reference frames will legitimately experience different temporal realities, with no single perspective privileged as the correct one. This relativistic view echoes ancient wisdom traditions that emphasized the role of perspective in shaping reality, while grounding this insight in precise mathematical relationships that can be tested through experiment. As we gaze outward into the cosmos, we look not only across vast distances, but also through the varied flows of time throughout the universe. What we observe is not a universal now, but a complex tapestry of moments, each occurring in its own local time frame, all woven together by the light that carries information from distant regions to our eyes and instruments. The stars and galaxies we see exist in their own temporal reference frames, connected to ours through the relativistic relationships that Einstein discovered. When we observe a galaxy billions of light years away, we see it not only as it was billions of years ago, due to the finite speed of light, but also as it existed in a temporal reference frame shaped by its own gravity and motion relative to us. This cosmic perspective on time's flexibility invites us to expand our imagination beyond the limitations of our everyday experience. The universe is stranger and more subtle than our intuitions suggest, with time itself varying its flow according to precise physical relationships. This realization is both humbling and exhilarating, reminding us of the limitations of our intuitive understanding while revealing the elegant mathematics that underlies cosmic reality. Time, like space, stretches and bends. It is not fixed, it flows differently everywhere. At the edge of a black hole, time approaches the boundaries of human understanding. These cosmic objects, where gravity reaches its most extreme expression, stretch and distort the fabric of space-time until our conventional notions of past, present, and future dissolve. Here, in the most warped regions of our universe, time reveals its most profound mysteries, challenging us to reimagine the nature of reality itself. Black holes represent the ultimate cosmic paradox, regions where matter has collapsed to such extreme density that nothing, not even light, can escape their gravitational pull beyond a boundary called the event horizon. First predicted by Einstein's general theory of relativity, and now observed throughout the universe, black holes come in various sizes, from stellar mass black holes formed from collapsed stars to supermassive behemoths lurking at the centers of galaxies, containing the mass of millions or billions of suns. Despite their name, black holes are not empty voids, but rather extraordinarily dense concentrations of matter. A stellar mass black hole might compress the mass of 5 suns into a region smaller than a city, while the supermassive black hole at the center of our Milky Way galaxy, Sagittarius A star, packs the mass of 4 million suns into a volume that could fit within the orbit of Mercury. This extreme concentration of mass creates the strongest gravitational fields in the universe, warping space-time so severely that it folds back upon itself. To understand what happens to time near and within these objects, we must venture beyond everyday intuition into the mathematics of general relativity, where time and space become inseparably entangled. Let us approach a black hole gradually, observing how time behaves at increasing proximity. Imagine we have 2 identical clocks, one aboard a spaceship gradually approaching a black hole, and another safely distant, monitored by astronomers. Both clocks initially tick at the same rate, marking seconds in perfect synchrony. As the spaceship ventures closer to the black hole, the distant astronomers, observing through their telescopes, would notice something strange. The clock aboard the approaching vessel would appear to tick increasingly slowly. This gravitational time dilation, a direct consequence of general relativity, becomes more pronounced as the ship nears the black hole's event horizon. For the astronomers watching from afar, time aboard the approaching ship seems to flow ever more sluggishly. If they could somehow maintain visual contact, they would see movements aboard the ship becoming progressively slower, as if the crew were moving through molasses. Electronic signals from the ship would arrive with decreasing frequency, their wavelength stretched by the black hole's gravitational field, in a process similar to redshift. As the ship approaches the critical distance of the event horizon, this slowing of time becomes extreme. From the distant observer's perspective, the clock aboard the ship would tick so slowly that it would appear nearly frozen. If they could still see the ship, it would appear to move in ultra-slow motion, with actions that might take seconds for the crew stretching out to minutes, hours, or even longer from the astronomer's viewpoint. At the event horizon itself, something remarkable happens in this observational framework. Time aboard the ship, as perceived by the distant astronomers, would appear to stop completely. The ship would seem frozen at the boundary, never quite crossing into the black hole, suspended in a moment that stretches towards eternity. The final light signals from the ship, just before it reaches the event horizon, would be infinitely redshifted and would take an infinite amount of time to reach the distant observers. This creates what physicists call the frozen star effect. From an external perspective, nothing ever quite crosses the event horizon of a black hole. Instead, infalling objects appear to slow asymptotically as they approach the boundary, creating a kind of time capsule at the horizon, preserving the final moments of everything that has ever fallen toward the black hole in a state of extreme time dilation. But what about from the perspective of the crew aboard the approaching ship? Their experience would be radically different. The crew members would notice no obvious changes in their own passage of time. Their clocks would seem to tick normally, their hearts would beat at regular intervals, and their thoughts would flow at ordinary rates. They would, however, observe strange effects when looking outward. As they draw nearer to the black hole, the crew would see the external universe accelerating. Light from distant stars would be blue-shifted, arriving at increased frequencies. If they could somehow maintain communication with the distant astronomers, they would receive messages at an increasingly rapid rate, as if the external universe were being fast-forwarded while they experienced time normally. This divergence of temporal experience highlights the relativity of simultaneity that Einstein discovered. There is no single universal now that connects the crew with the distant astronomers. Each exists in their own reference frame, with its own equally valid flow of time. Neither perspective is more correct than the other. Both the apparently frozen ship seen by distant observers and the normally functioning ship experienced by the crew represent valid descriptions of the same physical reality viewed from different reference frames. As the ship crosses the event horizon, the crew would notice no dramatic change in their local experience. There is no physical barrier or membrane marking the horizon, no sudden jolt or discontinuity in the fabric of space-time from their perspective. The event horizon is a mathematical boundary rather than a physical one, defined simply as the point beyond which light cannot escape to the external universe. Yet the crossing of this invisible boundary represents a profound transition. Once past the event horizon, the crew cannot send signals to the outside universe. Light emitted outward from their ship would fall back toward the black hole's center, trapped by the extreme curvature of space-time. Stranger still, the geometry of space-time inside the event horizon transforms in ways that challenge our intuitive understanding of space and time. Inside a black hole, the roles of space and time begin to interchange. The dimension we normally experience as time becomes space-like, while one of the spatial dimensions takes on time-like properties. This means that motion toward the center of the black hole becomes as inevitable as the forward flow of time is in our ordinary experience. Just as we cannot help moving from the past toward the future in our everyday lives, an object inside a black hole's event horizon cannot help moving toward the singularity at its center. The singularity represents the ultimate destination for anything that enters a black hole, a point where, according to classical general relativity, matter is compressed to infinite density and space-time curvature becomes infinite. At the singularity, our current physical theories break down completely. The mathematics yields infinities and paradoxes rather than meaningful predictions, suggesting that we need a more comprehensive theory, likely one that unifies general relativity with quantum mechanics to describe what truly happens there. Many physicists believe that the singularity predicted by classical general relativity is never actually reached, that quantum gravitational effects would intervene before matter could be compressed to a mathematical point. Various approaches to quantum gravity, including string theory and loop quantum gravity, suggest different possible fates for matter that falls into a black hole, but none has yet been confirmed observationally. What happens to time at this central region remains one of the greatest mysteries in physics. Does time end at the singularity? Does it transform into something else entirely? Or does quantum gravity reveal new possibilities? Perhaps even connections to other regions of space-time or other universes entirely? These questions lie at the frontier of theoretical physics, where our mathematical models reach their limits and must give way to new, as yet undiscovered principles. Beyond these theoretical considerations, what would it actually be like to fall into a black hole? For a human observer, the experience would be both sublime and fatal. As you approached a large black hole, you would first notice the distortion of the star field behind it, as the black hole's gravity bends light passing nearby in a process called gravitational lensing. Stars that should be hidden behind the black hole would appear displaced, forming a ring of light around the dark central region. This dark region, called the black hole's shadow, is not the event horizon itself, but the area where light paths orbit or fall into the black hole, rather than reaching the observer. For a supermassive black hole like Sagittarius, a star at the center of our galaxy, this shadow would appear approximately 50 micro-arcseconds across when viewed from Earth, about the size of a donut on the Moon as seen from Earth. In April 2019, the Event Horizon Telescope collaboration captured the first image of such a shadow from the supermassive black hole at the center of the galaxy M87, providing dramatic visual confirmation of Einstein's predictions. As you moved closer to the black hole, tidal forces would become increasingly significant. These forces arise from the difference in gravitational pull between the parts of your body closer to and farther from the black hole. For a sufficiently large black hole, these tidal forces might remain survivable even as you cross the event horizon, allowing you to pass into the black hole's interior without immediate physical destruction. Once inside, you would have a finite amount of proper time, as measured by your own watch, before reaching the central region where tidal forces would become overwhelming. For a supermassive black hole like the one at the center of our galaxy, this might give you minutes or even hours of existence inside the event horizon before the inevitable end. During this time, you would observe the outside universe compressed into a small, bright circle above you, growing dimmer as you fell deeper, while ahead of you stretched the darkness of the black hole's interior. Throughout your descent, you would experience time normally according to your own clock, even as observers outside the black hole would see your image frozen at the event horizon, slowly fading from view as your light becomes increasingly redshifted. This divergence between your experience and that of external observers represents one of the most profound temporal disconnections possible in our universe. The fate of information that falls into a black hole has troubled physicists for decades, leading to what is known as the black hole information paradox. Quantum mechanics suggests that information cannot be destroyed, yet the classical description of black holes implies that any information about the specific details of matter falling in would be lost, leaving only the black hole's mass, charge, and angular momentum as observable properties. Stephen Hawking's discovery that black holes emit radiation, now called Hawking radiation, complicated this picture further. This radiation, a quantum effect occurring near the event horizon, causes black holes to lose mass slowly over time and eventually evaporate completely. But does this radiation carry out information about what fell in, or is that information truly lost? Physicists continue to debate this question, with implications for the foundations of both quantum mechanics and general relativity. Recent theoretical advances suggest possible resolutions to the information paradox, including the idea that information might be preserved in subtle quantum correlations within the Hawking radiation, or that information might be stored in a kind of holographic manner on the event horizon itself. These approaches draw on concepts from string theory and quantum information theory, hinting at deeper connections between gravity, quantum mechanics, and information that we are only beginning to understand. The temporal strangeness of black holes extends beyond their event horizons to affect the space-time around them, particularly for rotating black holes. Most black holes in the universe likely rotate, inheriting angular momentum from the matter that formed them. This rotation drags space-time around with it in a process called frame dragging. creating a region outside the event horizon called the ergosphere. Within the ergosphere, space-time rotates at such a speed that no object can remain stationary relative to distant stars. Everything within this region is forced to co-rotate with the black hole, as if caught in a whirlpool of space-time. This rotational energy can actually be extracted through a process called the Penrose process, where an object splitting in two within the ergosphere can result in one fragment escaping with more energy than the original object possessed, effectively extracting energy from the black hole's rotation. For maximally rotating black holes, theoretical structures called closed time-like curves might be possible, at least mathematically. These curves represent paths through space-time that return to their starting points not just in space, but also in time, essentially forming time loops. While most physicists believe that some as yet undiscovered principle would prevent the actual formation of such curves, their presence in the mathematics of rotating black holes highlights the profound connection between these objects and the fabric of time itself. Beyond these mind-stretching theoretical considerations, black holes play crucial roles in the evolution of galaxies and the overall cosmic story. The supermassive black holes at galactic centers co-evolve with their host galaxies, influencing star formation and galactic structure through the energy released as matter falls into them. When galaxies merge, their central black holes eventually coalesce as well, releasing enormous amounts of energy as gravitational waves, ripples in the fabric of space-time itself. The detection of gravitational waves from merging black holes by the LIGO and Virgo collaborations, first announced in February 2016, opened a new window on the universe, allowing us to perceive cosmic events through distortions in space-time rather than through light or other electromagnetic radiation. These observations have confirmed key predictions of general relativity while revealing a population of black holes with masses and merger rates that continue to refine our understanding of these extraordinary objects. Perhaps the most profound implication of black holes for our understanding of time comes from considering their ultimate fate. According to Hawking's work, black holes are not truly eternal, but evaporate through the emission of radiation, with smaller black holes evaporating more quickly than larger ones. A stellar mass black hole might take about 10 to the power of 67 years to evaporate completely, far longer than the current age of the universe, while the supermassive black holes at galactic centers would last even longer. This evaporation process can be understood as a transformation of the black hole's mass energy into thermal radiation through quantum processes occurring near the event horizon. As the black hole loses mass, its temperature increases, accelerating the evaporation process. In its final moments, a black hole would release an enormous burst of energy, briefly outshining galaxies before disappearing completely. What happens at the final moment of a black hole's existence? Does the singularity somehow resolve itself, revealing new physics beyond our current understanding? Does the information that fell into the black hole over its lifetime somehow re-emerge in the final radiation? These questions remain unanswered, pointing toward a more complete theory of quantum gravity that might reconcile the seemingly contradictory implications of quantum mechanics and general relativity. The existence of black holes reminds us that time itself had a beginning and may have an end. Just as the event horizon of a black hole marks a boundary beyond which the normal flow of time as we understand it breaks down, the Big Bang represents a temporal boundary at the beginning of our universe, before which our current physical theories cannot meaningfully describe reality. Similarly, the far future evolution of the cosmos, perhaps toward a state of maximum entropy where no further organized activity is possible, suggests a potential ending of cosmic time, or at least of time as a meaningful measure of change. Black holes thus serve as both physical objects of extraordinary interest and profound metaphors for the limits of our understanding of time. At their boundaries, time stretches toward infinity from an external perspective, while continuing to flow normally for those crossing the threshold, never to return or communicate their experience. Inside, the very distinction between time and space transforms, revealing the deeper unity of space-time underlying our usual perception of separate dimensions. These cosmic objects, where matter has fallen into its own gravitational well so deeply that it vanishes from our observable universe, leaving only its mass, charge, and angular momentum as detectable properties represent the most extreme environments known to science. Yet they are not rare cosmic oddities, but fundamental components of galaxies, including our own, shaping the evolution of the cosmos through their gravitational influence and the energy released as matter falls into them. As we contemplate black holes, we confront the limits of our intuition about space and time. We discover that the seemingly solid ground of our temporal experience, the steady tick of clocks and flow of moments from past to future, dissolves in the extreme curvature of space-time near these objects. We find that different observers can have radically different but equally valid experiences of the same events, with no single perspective privileged as the correct one. This relativistic view of time, pushed to its extreme near black holes, invites us to expand our understanding beyond the limitations of our everyday experience. Time is not uniform throughout the cosmos, but varies its flow according to the distribution of matter and energy, the curvature of space-time, and the motion of observers. In the everyday world, these variations are too small to notice without precise instruments. But near a black hole, they become the dominant reality, stretching time to infinity at the event horizon for distant observers while allowing it to flow normally for those crossing this boundary of no return. This discrepancy is not a paradox to be resolved, but a feature of reality to be understood, a consequence of the deep unity between space, time, gravity, and motion revealed by Einstein's theories. As we contemplate these profound aspects of black holes, we might reflect on how they mirror certain aspects of human experience. We all cross personal event horizons throughout our lives, boundaries beyond which we cannot return to our former states or communicate completely what we have experienced to those who remain behind. Birth, death, profound love, spiritual awakening, all mark transitions that transform us in ways that cannot be fully conveyed to others. Like the event horizon of a black hole, these personal transitions create asymmetries in understanding between those who have crossed over and those who observe from a distance. Perhaps in this metaphorical sense, we can find a connection between the cosmos at its most extreme and our own journeys through the mysterious dimension we call time. Near the abyss, time becomes a question, not a certainty. Time flows in one direction. This simple observation, so fundamental to our daily experience that we rarely question it, conceals profound mysteries at the heart of physics. We remember the past, but not the future. We can create records and artifacts that persist through time, allowing future generations to learn about earlier eras. Eggs break, but broken eggs never spontaneously reassemble. Coffee cools, ice melts, and stars burn out. Throughout the cosmos, processes unfold in a specific temporal direction, defining what physicists call the arrow of time. Yet when we examine the fundamental laws of physics, we encounter a puzzling symmetry. Most of the basic equations that govern matter and energy work equally well running forward or backward in time. The laws of classical mechanics, electromagnetism, and even quantum mechanics are essentially time-symmetric, showing no preference for one temporal direction over another. A film of two billiard balls colliding, played in reverse, shows nothing that violates the laws of physics. This disconnect between time-symmetric laws and our time-asymmetric experience represents one of the deepest puzzles in modern science. Why does time appear to flow in only one direction when the underlying physical laws seem to permit either? What gives time its arrow, its unmistakable direction from past to future? To explore this question is to probe the very nature of time itself. The most widely accepted explanation for time's arrow lies in thermodynamics, specifically in the concept of entropy. Entropy measures the disorder or randomness of a system, or more precisely, the number of different microscopic arrangements that correspond to the same macroscopic state. The second law of thermodynamics, formulated in the 19th century, states that the total entropy of an isolated system never decreases over time. This principle explains many everyday observations. A drop of ink disperses in water rather than concentrating itself. A hot cup of coffee cools to room temperature rather than growing hotter. A house becomes messy without intervention, but never spontaneously tidies itself. In each case, the system naturally evolves from a less probable, more ordered state to a more probable, less ordered state. The Austrian physicist Ludwig Boltzmann provided the microscopic foundation for this principle, showing how entropy emerges from the statistical behavior of countless particles. In Boltzmann's view, high-entropy states are simply more probable than low-entropy states because there are many more ways for particles to be arranged randomly than in specific ordered configurations. A deck of cards has only one arrangement that corresponds to being perfectly sorted by suit and number, but billions of possible arrangements that appear randomly shuffled. According to this perspective, the arrow of time points in the direction of increasing entropy. We perceive time flowing from past to future because we observe systems evolving from less probable to more probable states. The broken egg has higher entropy than the whole egg, so we see eggs breaking but never unbreaking. The mixed ink and water has higher entropy than the separated ink and water, so we see mixing but not unmixing. But this statistical explanation raises a deeper question. If systems naturally evolve toward higher entropy states simply because there are more such states available, why wasn't the universe already in a maximum entropy state from the beginning? What set the initial conditions that allowed for the lower entropy past from which our present has evolved? The answer appears to lie in cosmology, in the unique conditions that prevailed near the beginning of our universe. Despite its tremendous energy density, the early universe was remarkably uniform, with matter and radiation distributed evenly throughout space, a condition of relatively low entropy. As the universe expanded and cooled, gravity began to pull matter together into increasingly complex structures, from gas clouds to stars, from stars to galaxies, from galaxies to clusters and superclusters. This gravitational clustering might seem to decrease entropy, creating more ordered structures from less ordered ones. But when gravity is properly accounted for in the entropy calculation, these aggregations actually represent an increase in total entropy. The gravitational field itself has entropy, and the overall process of structure formation, from the smooth early universe to the clumpy cosmos we observe today, follows the second law of thermodynamics. The universe's initial low entropy state remains somewhat mysterious. Some cosmologists, including Roger Penrose, have suggested that the smooth, uniform conditions of the early universe represent an extraordinary cosmic coincidence requiring a new physical principle to explain. Others propose that our observable universe is just one region of a much larger multiverse with varying entropy conditions, and we naturally find ourselves in a region where entropy was once low enough to permit the emergence of life and consciousness. Regardless of its ultimate explanation, this cosmic arrow of time, flowing from the low entropy early universe toward a higher entropy future, appears to underlie all other temporal arrows we observe, from the thermodynamic arrow of cooling coffee to the psychological arrow of remembering the past but not the future. Our memories and records of the past depend critically on the second law of thermodynamics. When we form a memory, we create physical changes in our brains, transforming them from a higher entropy state where many outcomes were possible to a lower entropy state that records one specific outcome. This process increases entropy in the broader environment, consistent with the second law, but creates local decreases in entropy that serve as records. Similarly, fossils, ancient texts, ice cores, and other historical artifacts represent local decreases in entropy that allow us to reconstruct the past. These records can only form and persist in a universe where entropy increases over time. In a hypothetical universe where entropy decreased, our conventional notions of causality would be reversed, with effects preceding causes and memories forming of events yet to occur. The relationship between entropy and information provides another perspective on time's arrow. Information can be understood as a measure of the reduction in uncertainty about a system. When we learn something new, we reduce our uncertainty, effectively decreasing the entropy of our knowledge state, while increasing entropy elsewhere through the physical processes involved in acquiring, processing, and storing that information. This information perspective helps explain why we remember the past, but not the future. Memories and records are physical systems that can store information about the past because they can be arranged in ways that correlate with past events. Such correlations form naturally as systems interact over time in an entropy-increasing universe. But correlations with future events would require either extraordinary coincidence or a violation of the second law of thermodynamics. The deep connection between entropy, information, and temporal asymmetry has led some physicists to suggest that the arrow of time might fundamentally be about information rather than just physical states. On this view, what makes the past different from the future is that we have information about the past encoded in the present, while the future remains open and undetermined, at least from our perspective. This informational view of time's arrow connects to quantum mechanics in intriguing ways. In quantum theory, systems exist in superpositions of possible states until measured or observed, at which point they appear to collapse into definite states. This process, known as quantum decoherence, involves the entanglement of quantum systems with their environments in ways that effectively transform quantum possibilities into classical probabilities. Decoherence happens extremely rapidly for macroscopic objects, explaining why we don't observe quantum superpositions in our everyday experience. Some physicists argue that this transition from quantum to classical behavior, with its apparent irreversibility and increase in entropy, may offer another perspective on the arrow of time, perhaps even a more fundamental one than classical thermodynamics alone. The quantum arrow of time relates to measurement and observation, processes that seem inherently time asymmetric. Once a quantum measurement is made, the system's state changes in ways that cannot be undone simply by reversing the physical motions of the particles involved. This irreversibility at the quantum level may contribute to the macroscopic arrow of time we experience in daily life. Beyond thermodynamics and quantum mechanics, several other domains exhibit distinctive temporal arrows that align with the cosmological arrow from low to high entropy. The radiative arrow of time describes how electromagnetic waves spread outward from sources rather than converging inward. Radio signals broadcast from Earth disperse into space, growing fainter with distance, but we never observe scattered radio waves spontaneously converging to form coherent signals. The biological arrow of time manifests in the processes of growth, development, aging, and evolution. Living organisms develop from simpler to more complex forms, age in characteristic ways, and eventually die and decompose. Species evolve and adapt to their environments over generations. These biological processes reflect the underlying thermodynamic arrow as organisms maintain their complex, low-entropy structures only by consuming energy and increasing entropy in their surroundings. The psychological arrow of time shapes our subjective experience of temporal flow. We perceive ourselves moving from past to future, never the reverse. Our consciousness seems to illuminate one moment after another in a steady progression that defines our sense of now. This experience present, neither entirely in the past nor fully in the future, moves forward in a way that feels inevitable and universal, though the details of temporal experience may vary across cultures and individuals. Some philosophers argue that this subjective flow of time is merely an illusion created by our consciousness, that the universe actually exists as a static four-dimensional block where all moments coexist equally, and our feeling of the present moving forward is just how our minds process this timeless reality. Others maintain that the flow of time is real and fundamental, not merely a psychological construct, but an essential feature of the cosmos. What makes this philosophical debate especially challenging is that both the block universe view, where time does not flow but simply exists all at once, and the flowing time view, where the present moment has special status, can be made consistent with our best physical theories. Neither position has been definitively ruled out by experiment or observation, leaving room for continued debate about the ultimate nature of temporal experience. The relationship between consciousness and time remains one of the great mysteries at the intersection of physics, neuroscience, and philosophy. Our awareness seems inherently temporal, unfolding moment by moment, in a way that aligns with the thermodynamic arrow. We remember the past, experience the present, and anticipate the future, never the reverse. This psychological arrow may be a consequence of how our brains process and store information in an entropy-increasing universe. Some researchers have suggested that consciousness itself might play a role in the apparent flow of time, that the moving now we experience might emerge from the way our awareness integrates information across short durations rather than instantaneously. On this view, the present moment as we experience it spans about 100 milliseconds of physical time, creating a moving window of now that gives rise to our sense of temporal flow. While the precise relationship between physical time and experienced time remains elusive, what seems clear is that the various arrows of time, from thermodynamic to quantum to biological to psychological, all align with the master arrow set by the universe's evolution from its low entropy beginning. This alignment is not coincidental, but reflects the deep connections between entropy, information, causality, and the structure of space-time itself. The puzzle of time's arrow becomes even more intriguing when we consider certain solutions to Einstein's equations of general relativity that appear to permit closed time-like curves, paths through space-time that return to their starting points not just in space but also in time. Such curves would effectively allow time travel into the past, creating potential paradoxes where effects might precede their causes. Most physicists believe that some yet undiscovered principle of quantum gravity would prevent the formation of closed time-like curves, enforcing what Stephen Hawking called the chronology protection conjecture, the idea that the laws of physics somehow conspire to prevent time travel and preserve our familiar causal structure where causes always precede their effects. But the fact that our best theory of gravity seems to allow for such possibilities highlights how much remains unknown about the fundamental nature of time. The search for a unified theory of quantum gravity, one that would reconcile quantum mechanics with general relativity, may ultimately provide deeper insights into the origin of time's arrow. Both leading approaches, string theory and loop quantum gravity, suggest that spacetime itself might emerge from more fundamental quantum processes, potentially explaining how our familiar temporal order arises from a deeper reality where conventional notions of time might not apply. While these theoretical frontiers remain speculative, the practical consequences of time's arrow shape our daily lives in countless ways. Our entire conceptual framework of causality, where causes precede effects, depends on the thermodynamic arrow. Our ability to learn from experience, to form memories, to create records and artifacts that persist through time, all rely on the entropy gradient established near the beginning of our universe. The arrow of time also shapes our emotional and existential experience of life. We feel nostalgia for the past, which we can remember but not change, and anxiety or hope about the future, which we can influence but not know with certainty. We experience grief at the irreversible loss of loved ones and the inevitable passage of our own lives from birth towards death. The one-way flow of time gives our existence both its poignancy and its preciousness. Yet despite its apparent inexorability, the arrow of time may not be absolute or eternal. In the far future of our expanding universe, as stars burn out and matter disperses, the cosmos may approach a state of maximum entropy or heat death, where organized structures have disappeared and meaningful change ceases. In such a state, with no further entropy increase possible, the thermodynamic arrow of time might effectively vanish, leaving only random fluctuations with no discernible direction. Alternatively, some speculative cosmological models suggest that our universe might eventually contract into a big crunch, potentially reversing the entropy gradient, and with it, the arrow of time. Others propose cyclic models where new universes emerge from the collapsed remains of previous ones, potentially resetting entropy and beginning new temporal arrows with each cycle. The far future remains as mysterious as the distant past, with our theories reaching the limits of their predictive power at both temporal extremes. What seems increasingly clear, however, is that time's arrow is not a simple autonomous feature of reality, but emerges from the interplay of entropy, information, quantum processes, and the unique cosmological conditions of our universe. This emergent nature of temporal asymmetry reminds us that time, despite its apparent simplicity in everyday experience, remains one of the most profound mysteries in science and philosophy. From the microscopic dance of quantum particles to the cosmic evolution of galaxies, from the formation of memories in our brains to the subjective flow of conscious experience, the one-way passage from past to future shapes every aspect of our reality. Yet, this temporal asymmetry arises from underlying physical laws that themselves show no preference for one-time direction over another. The equations of fundamental physics, from Newton's laws of motion to the Schrödinger equation of quantum mechanics, work equally well when the direction of time is reversed. Only when we consider entropy, probability, and the initial conditions of our universe does the preferred direction of time emerge. This tension between time-symmetric laws and time-asymmetric experience continues to inspire new approaches to understanding the nature of time itself. Some theorists propose that time might be discrete rather than continuous at the smallest scales, chunked into indivisible units rather than flowing smoothly. Others suggest that time might be an emergent property rather than a fundamental dimension, arising from deeper quantum entanglement structures in a way analogous to how temperature emerges from the collective motion of particles. Still others explore the possibility that our conventional notion of linear time might be too limited, that the true structure of temporal reality might involve multiple dimensions of time, branching timelines or more exotic configurations that our evolution-prepared brains struggle to conceptualize. These speculative frontiers remind us that our intuitive understanding of time, shaped by our mesoscale experience in a moderate entropy gradient, may capture only a limited aspect of a deeper temporal reality. Despite these theoretical uncertainties, the practical reality of time's arrow remains inescapable in our daily experience. We age in one direction only. Broken cups do not reassemble. Memories form of the past, not the future. Our lives unfold along a one-way path from birth to death, giving urgency and significance to our choices, which can influence the future but cannot change what has already occurred. This irreversibility creates both the tragedy and the beauty of the human condition. We cannot return to the past to correct mistakes or relive joyful moments, but this very limitation gives meaning to our decisions and poignancy to our experiences. In a universe with a bidirectional time arrow, where effects could precede causes and the future could influence the past, the entire fabric of our existential experience would be unrecognizably transformed. The arrow of time thus remains both a scientific puzzle and an existential foundation of human experience. It emerges from the statistical behavior of countless particles and the cosmological conditions of our universe, yet shapes our consciousness, our identity, and our understanding of reality at the most intimate level. We are creatures of time's arrow, our existence inseparable from the one-way flow from past to future that defines our cosmos. As we contemplate the grand temporal journey of our universe, from its remarkably uniform beginning to its potential heat death in the far future, we find ourselves at an intermediate point in this cosmic story. We exist in a universe organized enough to support the complex structures of life and consciousness, yet disordered enough to contain the entropy gradient that gives time its direction. This intermediate position allows us to look backward in time through records, artifacts, and the light from distant galaxies, reconstructing the history of our cosmos. It also allows us to look forward, projecting potential futures based on our understanding of physical laws and initial conditions. We stand at a unique vantage point in cosmic history, capable of comprehending both the arrow of time and the timeless laws that give rise to it. Perhaps the greatest wonder is that in a universe governed by entropy, where disorder naturally increases, complex structures like stars, planets, living organisms, and conscious minds have emerged along the way. These islands of order exist not in violation of the second law, but because of it, as open systems that maintain their complexity by increasing entropy in their surroundings, riding the current of time's arrow rather than opposing it. Our consciousness, with its capacity to perceive, remember, and anticipate, represents one of the most remarkable developments along time's journey. We are the universe becoming aware of itself and its temporal nature, capable of tracing our origins back to the early cosmos and projecting our potential futures toward the distant horizon of time. Through science, art, philosophy, and shared human experience, we explore the many dimensions of temporal existence, finding meaning in our brief moment within the vast current of cosmic time. Time flows forward because the universe forgets how to go back. At the smallest scales of existence, where the strange rules of quantum mechanics govern reality, time reveals its most puzzling aspects. The quantum world challenges our intuitive understanding of time as a smooth, continuous flow, suggesting instead a realm where temporal relationships blur, causality becomes ambiguous, and the very notion of before and after may lose its fundamental meaning. In this microscopic domain, time behaves with a subtlety and flexibility that forces us to reconsider its true nature. Quantum mechanics, developed in the early 20th century by pioneers like Max Planck, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, describes the behavior of matter and energy at atomic and subatomic scales. This revolutionary framework has proven extraordinarily successful at predicting experimental results and has enabled countless technological innovations, yet it presents a picture of reality that seems profoundly alien to our everyday experience, nowhere more so than in its treatment of time. In classical physics, time serves as a simple parameter against which change occurs. Particles follow definite trajectories through space as time advances, and if we know a system's initial conditions with perfect precision, we can, in principle, predict its future states with perfect accuracy. Time flows uniformly, and events occur in a definite sequence. Quantum mechanics shatters this comfortable picture. According to the standard interpretation, quantum systems do not exist in definite states before measurement, but in superpositions of multiple possible states simultaneously. A particle may effectively be in several locations at once, or spinning in multiple directions at the same time, until observed or measured, at which point it somehow resolves into one definite state. This quantum indeterminacy creates profound questions about the nature of time. If a particle exists in a superposition of states until measured, what does it mean to speak of its position or momentum at a particular time before measurement? How do quantum systems evolve through time when their properties lack definite values? And how does the apparent randomness of quantum measurement outcomes relate to our understanding of causality, where effects follow causes in temporal sequence? The time evolution of quantum systems between measurements is governed by the Schrödinger equation, a deterministic wave equation that describes how quantum states change over time. Unlike classical systems, the quantum wave function represents probabilities rather than definite physical properties, and its evolution describes the changing landscape of possibilities rather than the definite trajectory of a particle. When measurement occurs, this smooth evolution appears to be interrupted by what physicists call wave function collapse, a sudden transition from multiple superposed possibilities to a single definite outcome. This collapse is not described by the Schrödinger equation and seems to introduce a fundamental discontinuity in the flow of time for quantum systems, a moment when the many possible futures contemplated by the wave function resolve into a single actuality. The nature of this collapse remains one of the great mysteries in quantum physics. In the Copenhagen interpretation, long the standard view among physicists, the collapse is treated as a fundamental, irreducible feature of reality, occurring instantaneously across the entire system being measured, regardless of its spatial extent. This instantaneous collapse sits uncomfortably with Einstein's relativity, which forbids faster than light transmission of information or causal influence. Alternative interpretations of quantum mechanics offer different perspectives on this collapse and its relationship to time. In the many worlds interpretation proposed by Hugh Everett III in 1957, the wave function never actually collapses. Instead, when what appears to be a measurement occurs, the universe branches into multiple realities, each containing one of the possible outcomes. In this view, all possible futures contemplated by the wave function actually occur in different branches of an ever-multiplying multiverse. The many worlds interpretation preserves the smooth, deterministic time evolution of the Schrödinger equation, but at the cost of a reality that branches into countless parallel timelines, most of which remain inaccessible to any single observer. Time in this view becomes a complex branching structure rather than a simple linear flow, with each quantum event spawning new temporal paths through a vast multiverse of possibilities. These competing interpretations of quantum mechanics, each with its own implications for the nature of time, remain empirically equivalent, predicting the same observable outcomes for all practical experiments. The choice between them remains primarily philosophical rather than scientific, a reminder that at the foundations of physics, our understanding of time intertwines with fundamental questions about reality, causality, and the limits of human knowledge. Beyond these interpretational debates lies the strange phenomenon of quantum entanglement, wherein two or more particles become correlated in ways that cannot be explained by classical physics. When particles are entangled, the measurement of one instantaneously affects the state of the other, regardless of the distance between them. Einstein, uncomfortable with this apparent violation of locality, called entanglement spooky action at a distance and viewed it as evidence that quantum mechanics must be incomplete. But subsequent experimental tests have confirmed that this spooky connection is indeed a feature of our universe, forcing us to reconsider our understanding of space, time, and causality. Entanglement suggests a reality where spatial separation does not necessarily imply causal independence. Entangled particles, even when separated by vast distances, behave as parts of a single system, their properties correlated in ways that cannot be explained by any influences traveling through space at or below the speed of light. This non-locality challenges our intuitive understanding of time as a framework in which causal influences propagate continuously through space. Some physicists have suggested that entanglement reveals a deeper level of reality where conventional notions of space and time break down. In this view, what appears to us as instantaneous action at a distance might actually reflect connections outside space-time as we understand it, pointing toward a more fundamental structure from which our familiar four-dimensional space-time emerges. The quantum Zeno effect provides another window into the strange temporal properties of quantum systems. This effect reveals that frequently observed quantum systems change more slowly than unobserved ones. In the extreme case, a continuously observed quantum system might freeze entirely, unable to change state at all. This connection between observation and temporal evolution has led some philosophers of physics to suggest that time itself might be observer-dependent at the quantum level, emerging from the interaction between quantum systems and their environments, rather than existing as an independent background parameter. On this view, the flow of time as we experience it might be intimately connected to the process of decoherence, whereby quantum systems lose their ability to exhibit interference effects through interaction with their surroundings. Decoherence helps explain why macroscopic objects behave classically rather than quantum mechanically. As quantum systems interact with their environments, information about their state spreads into the surroundings in a way that makes quantum coherence increasingly difficult to maintain or observe. This process effectively transforms quantum superpositions into classical probability distributions, creating the appearance of wave function collapse without requiring it as a fundamental postulate. The irreversibility of decoherence connects quantum mechanics to thermodynamics and the arrow of time. Once quantum coherence has leaked into a complex environment, reversing the process would require precise control over countless environmental degrees of freedom, a practical impossibility analogous to the improbability of seeing scattered ink particles spontaneously gather back into a drop. In this way, quantum decoherence aligns with and perhaps underlies the thermodynamic arrow of time discussed in the previous chapter. The temporal puzzles of quantum mechanics deepen further when we consider the quantum measurement problem itself. The standard formulation of quantum mechanics treats measurement as a special process occurring outside the quantum system being measured, a perspective that creates an uncomfortable divide between the observer and the observed. But observers themselves are physical systems subject to the laws of quantum mechanics, creating a regress that challenges the consistency of the theory. The very ability to measure, observe, and record may be inseparable from the directional flow of time. Measurement creates information that propagates forward in time, from the measured system to the measuring apparatus to the broader environment, aligning with the thermodynamic arrow. The temporal asymmetry of measurement, like the asymmetry of memory and record formation, may ultimately derive from the cosmological initial conditions that established our universe's entropy gradient. In quantum field theory, the extension of quantum mechanics that deals with fields like the electromagnetic field, particles are understood not as primary objects, but as excitations in underlying quantum fields that permeate all of space-time. This field perspective reveals the quantum vacuum as a seething sea of virtual particles that continually pop in and out of existence, borrowing energy from the vacuum for brief periods permitted by Heisenberg's uncertainty principle. The behavior of virtual particles suggests a picture where even seemingly empty space contains a complex quantum structure with its own temporal patterns. The vacuum fluctuations occur on incredibly brief timescales, approaching the Planck time where our current theories break down entirely. At these extremely short durations, the very concept of time as a continuous flow may need revision. Some approaches to quantum gravity, attempting to reconcile quantum mechanics with Einstein's general relativity, suggest that space-time itself might have a discrete granular structure at the smallest scales. Loop quantum gravity, for instance, proposes that space is woven from tiny loops or links, with a minimum possible length, area, and volume. In such theories, time too might come in indivisible units rather than flowing continuously, with the Planck time, about 10 to the negative 44 seconds, representing the smallest meaningful duration. This quantum granularity of time would be entirely imperceptible in ordinary experience, just as the atomic nature of matter remains invisible to our unaided senses, but it would fundamentally change our understanding of time's nature, suggesting that the apparently smooth flow we experience emerges from a deeper, discrete reality, much as the apparently smooth flow of a movie emerges from a rapid sequence of distinct frames. Even more radical approaches to quantum gravity suggest that space-time itself might emerge from more fundamental entities, like causal relationships between events. In these views, time is not a primary dimension, but emerges from the network of causal connections, with temporal order reflecting the pattern of what can influence what. Such theories hint at a reality where causality is more fundamental than time itself, a profound inversion of our conventional understanding. Perhaps the most profound temporal mystery in quantum physics arises from the Wheeler-DeWitt equation, an attempt to apply quantum mechanics to the universe as a whole. This equation suggests that in a complete quantum theory of gravity, the wave function of the universe would not depend on time at all. Time would disappear from the fundamental description of reality, existing only as an approximate emergent feature of our experience. This problem of time in quantum gravity remains unsolved, with various approaches offering different perspectives on how our experienced flow of time might emerge from a timeless fundamental reality. Some propose that time emerges through the entanglement of subsystems within the universe, with our perception of change reflecting the correlations between different parts of an essentially static whole. Others suggest that time might be related to the growth of complexity or information within a quantum system, a perspective that connects to thermodynamics and the arrow of time. The temporal puzzles of quantum mechanics have been confirmed through numerous experiments, including the famous delayed choice experiments first proposed by John Wheeler. In these experiments, the decision whether to measure which path a particle took through a double-slit apparatus or to observe its interference pattern can be delayed until after the particle has passed through the slits, yet still affects the observed outcome. In the most dramatic versions of these experiments, the measurement choice can be determined by quantum random number generators, whose outcomes were not determined when the particle passed through the slits. These experiments suggest that in the quantum realm, the temporal sequence of cause and effect becomes blurred, with future measurement choices seemingly influencing past particle behavior. The results of delayed choice experiments do not actually allow information to be sent backward in time, preserving causal order at the level of observable signals. But they do suggest that quantum reality does not fit neatly into our conventional notions of temporal sequence, where causes must precede their effects. At the quantum level, temporal relationships appear more subtle and complex than our everyday experience would suggest. Similar temporal strangeness appears in quantum eraser experiments, where measurement results that should reveal which path a particle took can be erased after the measurement has occurred, restoring interference patterns that should have been destroyed by the which path information. These experiments highlight the role of information in quantum mechanics and suggest that the temporal sequence of information acquisition, rather than the physical sequence of interactions, determines quantum behavior. These quantum peculiarities do not allow for practical time travel or the violation of causality at the macroscopic level. The formalism of quantum mechanics ensures that no observable signals can travel faster than light, preserving Einstein's relativistic prohibition against causal paradoxes. But they do suggest that at the quantum level, temporal relationships might be more flexible and subtle than our classical intuitions allow. As we contemplate these quantum puzzles, we are reminded that time at the smallest scales may be fundamentally different from our everyday experience. The quantum world suggests a reality where temporal sequence becomes probabilistic rather than definite, where causality operates through correlations that transcend spatial separation, and where the very concept of before and after may emerge from more fundamental relationships rather than existing as primary features of reality. Yet despite these quantum mysteries, our lived experience of time maintains its apparent flow, carrying us from past to future in what feels like a smooth, continuous progression. The quantum strangeness at microscopic scales somehow averages out to produce the familiar temporal reality we navigate daily, where causes precede effects, memories record the past but not the future, and the second law of thermodynamics governs the evolution of physical systems. This emergence of classical temporality from quantum foundations remains incompletely understood, a reminder that time continues to challenge our deepest theories and most sophisticated mathematics. The quantum puzzle of time is not merely a scientific curiosity, but a window into the fundamental nature of reality, inviting us to expand our concepts beyond the limitations of everyday experience into the profound strangeness of the quantum world. At the smallest scale, time flickers, uncertain, unfinished. Life and time are inextricably interwoven. Unlike the inanimate matter from which living things emerge, life exists as a process unfolding through time, rather than as a static state. From the simplest bacteria to the most complex mammals, living organisms embody time in their metabolic rhythms, reproductive cycles, developmental sequences, and evolutionary trajectories. In this chapter, we explore how time shapes life at every scale, and how living things have evolved to measure, respond to, and even manipulate time to their advantage. Life on Earth began approximately 3.5 billion years ago, emerging from complex chemical systems that somehow crossed the threshold from non-living to living. This transition marked a profound shift in how matter interacts with time. While non-living systems passively experience time's flow, living systems actively track it, synchronize with its rhythms, and pass information forward through generations, creating a biological memory that extends far beyond the lifespan of any individual organism. At the most fundamental level, life represents a temporary victory against the thermodynamic arrow of time. The second law of thermodynamics dictates that isolated systems evolve toward increasing entropy or disorder, yet living things maintain and even increase their internal order by importing energy from their environment and exporting waste. They exist as islands of decreasing entropy in a sea of increasing disorder, not violating the second law, but creating local exceptions through their continuous exchange with the environment. Every living cell contains an intricate chemical choreography precisely timed to maintain life. Enzymes accelerate reactions that would otherwise take years to occur naturally, allowing them to happen in fractions of seconds. Transport proteins move molecules across membranes in carefully regulated sequences. DNA replication proceeds with astonishing speed and accuracy, copying billions of base pairs with only a handful of errors. Each of these processes depends on exquisite temporal coordination, with molecules arriving at the right place at exactly the right time. Beyond these cellular timekeepers, most organisms possess specialized mechanisms for tracking time at larger scales. Circadian clocks, present in organisms from cyanobacteria to humans, maintain an internal rhythm of approximately 24 hours, synchronizing physiological processes with the daily cycle of light and darkness. These biological clocks continue to function even in constant conditions, demonstrating that they are internal to the organism rather than mere responses to external cues. In mammals, the master circadian clock resides in the suprachiasmatic nucleus of the hypothalamus, a tiny brain region containing about 20,000 neurons that synchronize their activity to create a coherent timekeeper for the entire body. This central clock coordinates a network of peripheral clocks in organs throughout the body, ensuring that processes like hormone release, metabolism, immune function, and sleep-wake cycles occur at appropriate times within the daily cycle. The circadian system illustrates a fundamental principle of biological time. Organisms do not simply react to temporal patterns in their environment, but actively anticipate them. A nocturnal rodent begins preparing for activity before sunset, producing enzymes needed for digestion and increasing alertness in advance of its nightly foraging. A plant initiates the molecular machinery for photosynthesis before dawn, ready to capture the first rays of sunlight. This anticipatory capacity provides a significant adaptive advantage, allowing organisms to prepare for regular environmental changes rather than merely responding after they occur. Beyond the daily cycle, many organisms track time across longer intervals. Plants and animals at mid to high latitudes respond to seasonal changes in day length, adjusting their physiology and behavior to prepare for summer abundance or winter scarcity. Migration, hibernation, mating, flowering, and leaf fall all occur in synchrony with these annual rhythms, creating the complex tapestry of seasonal life that characterizes most ecosystems. Some organisms track time across even longer intervals. Cicadas of the genus Magicicada emerge from the ground in massive numbers after precisely 13 or 17 years of underground development. These prime number cycles are thought to help the cicadas avoid synchronizing with predator population cycles. Similarly, many plants produce seeds that remain dormant for years or decades, germinating only when specific environmental conditions indicate a high probability of successful growth and reproduction. The ability to measure and respond to time extends to shorter intervals as well. Many predator-prey interactions unfold over seconds or minutes, with split-second timing determining whether a predator captures its meal or goes hungry. Courtship displays, territorial contests, and other social interactions often involve precisely timed sequences of behavior that communicate information about identity, intention, or quality to other individuals. The diversity of biological timing mechanisms reveals time as a fundamental dimension of natural selection. Organisms that can accurately track time and synchronize their activities with temporal patterns in their environment gain significant advantages in survival and reproduction. This selective pressure has led to the evolution of multiple, partially redundant timing systems operating across different scales, from the millisecond precision of neural firing to the multi-year cycles of reproductive timing. Perhaps the most profound temporal dimension of life is its evolutionary history, stretching back through billions of years of descent with modification. Evolution itself can be understood as a process that unfolds through time, with genetic variations arising in each generation, and natural selection filtering these variations based on their effects on survival and reproduction. The accumulation of these selected changes over countless generations has transformed the simplest early life forms into the astonishing diversity of organisms that inhabit our planet today. The fossil record provides a window into this deep, evolutionary time, allowing us to observe the major transitions in life's history: the emergence of multicellularity, the colonization of land, the evolution of flight, the rise and fall of dinosaurs, and countless other transformations that have shaped our biosphere. Each fossil represents an organism frozen in time, a single frame in the great evolutionary film that continues to unfold around us. Modern molecular techniques have added new dimensions to our understanding of evolutionary time. By comparing the DNA sequences of different species, scientists can construct phylogenetic trees showing the pattern of evolutionary relationships and estimate the timing of evolutionary divergences. These molecular clocks reveal that humans and chimpanzees shared a common ancestor approximately 6 million years ago, that mammals began their adaptive radiation after the extinction of non-avian dinosaurs 66 million years ago, and that the last universal common ancestor of all current life on Earth lived perhaps 4 billion years ago. The study of evolutionary developmental biology has revealed how changes in the timing of developmental processes have played a crucial role in evolutionary change. Many significant evolutionary innovations resulted not from the invention of entirely new genes or structures, but from modifications to the timing of developmental events. For instance, the retention of juvenile characteristics into adulthood, a process called pedomorphosis, has contributed to the evolution of humans by extending the period of brain growth and delaying the closure of skull sutures compared to our evolutionary relatives. At the scale of individual organisms, development represents another fundamental temporal dimension of life. From the fertilized egg to the mature adult, organisms undergo a precisely choreographed sequence of changes in form and function. This developmental trajectory emerges from the complex interaction between genetic regulatory networks and environmental signals over time. Human development illustrates the intricate temporal organization of life particularly clearly. After fertilization, the zygote undergoes a series of precisely timed cell divisions. Gastrulation, the process that establishes the 3 primary germ layers, begins around the 14th day. Organogenesis, the formation of basic organs, occurs primarily between weeks 3 and 8, with different organ systems developing in a carefully orchestrated sequence. Throughout this developmental process, earlier events create the conditions necessary for later ones, establishing a causal chain that unfolds through time. The proper timing of these events depends on complex gene regulatory networks that activate and deactivate specific genes at precisely the right moments, creating a molecular narrative that guides the embryo from simplicity to complexity. Birth marks a dramatic transition in human temporal experience, from the relatively constant environment of the womb to the complex rhythms of the external world. The newborn must rapidly adapt to the cycle of day and night, developing a circadian rhythm that will influence nearly every aspect of physiology and behavior throughout life. Human psychological development similarly follows a temporal sequence, with different cognitive abilities emerging at characteristic ages. Infants develop object permanence around 7 to 8 months. Language typically emerges around 1 year and rapidly expands during the 2nd year of life. Theory of mind, the understanding that others have mental states different from one's own, generally develops between ages 3 and 5. Abstract reasoning, long-term planning, and full impulse control continue to develop through adolescence and into early adulthood as the prefrontal cortex matures. The human lifespan itself reflects evolutionary compromises regarding temporal allocation. Unlike some organisms that reproduce once and die immediately afterward, humans have evolved a life history strategy characterized by extended childhood, relatively late reproduction, and a significant post-reproductive period. This pattern allows for complex learning during childhood and adolescence, continued care of offspring during the reproductive years, and transfer of knowledge and resources to younger generations during the post-reproductive period. The evolution of this distinctively human life history pattern involves significant changes in developmental timing compared to our closest evolutionary relatives. Humans experience a longer period of fetal brain growth, a more extended childhood, and a later onset of puberty than other great apes. We also show distinctive patterns of aging, with females undergoing menopause decades before the end of the typical lifespan, a relatively unusual feature in the animal kingdom. These life history adaptations reflect the temporal trade-offs inherent in biological systems. Energy and resources allocated to growth cannot simultaneously be used for reproduction. Time spent learning delays reproduction, but may improve survival and reproductive success later in life. The finite nature of time forces living systems to make strategic allocations, creating different patterns of growth, reproduction, and aging across species. Aging itself represents one of the most profound temporal challenges for living systems. Despite the remarkable ability of organisms to maintain themselves against entropy, this maintenance is never perfect. Over time, damage accumulates in cells and tissues from both external insults and internal metabolic processes. DNA mutations, protein cross-linking, telomere shortening, and mitochondrial dysfunction gradually impair cellular function, leading to the progressive decline we recognize as aging. Various evolutionary theories have been proposed to explain why aging occurs, despite its obvious disadvantages for individual organisms. According to the mutation accumulation theory, harmful mutations that affect only older individuals experience weaker selection pressure because fewer individuals survive to the age where these mutations have effects. The antagonistic pleiotropy theory suggests that genes beneficial in early life may have harmful effects later, and will be favored by selection if the early benefits outweigh the later costs. Whatever its evolutionary origins, aging confronts us with the finite nature of biological time. Unlike some simpler organisms like Hydra that show negligible senescence, maintaining themselves indefinitely through continuous cell replacement, complex animals with specialized tissues face intrinsic limits to their duration. No amount of medical intervention can currently prevent the eventual accumulation of damage that characterizes biological aging. Death represents the final temporal boundary of individual existence, the point at which a living system can no longer maintain itself against entropy. Yet even this boundary is somewhat blurred in biological systems. Clinical death, the cessation of heartbeat and breathing, can sometimes be reversed if circulation is restored quickly enough. Brain death provides a more definitive boundary, but even then, individual cells and tissues may remain viable for hours or days with proper support. Moreover, death at the organism level does not necessarily mean the end of all biological continuation. Through reproduction, organisms pass genetic information to their offspring, creating a form of temporal extension beyond individual lifespan. Some organisms achieve a more direct form of continuity through asexual reproduction, with offspring that are genetic clones of the parent. Human beings have developed additional strategies for extending their influence beyond biological death. Through language, writing, and other forms of cultural transmission, humans can pass knowledge, values, and ideas to subsequent generations. Through social structures like families, communities, and institutions, they can create systems that persist beyond individual lives. Through art, science, technology, and other creative endeavors, they can leave legacies that continue to affect the world long after their biological existence has ended. These various forms of continuation beyond death reflect the deep relationship between life and time. Living things are not static objects, but dynamic processes extended through time, with boundaries that may be clear at some scales, but blurred at others. An individual human being is simultaneously a temporary arrangement of matter, a link in an unbroken chain of genetic descent stretching back billions of years, and a node in a vast network of cultural and ecological relationships extending into the future. Our subjective experience of time reflects this biological embeddedness. We perceive time through the lens of our circadian rhythms, our developmental stage, our memories of the past, and our anticipations of the future. Our temporal perception expands and contracts with our physiological and emotional states, speeding up during emergencies when rapid processing is advantageous, slowing down during novel or significant experiences that merit detailed encoding in memory. This biological foundation of temporal experience reminds us that time is not merely an external dimension in which life exists, but an integral aspect of what it means to be alive. From the biochemical oscillations that regulate cellular processes to the evolutionary changes that unfold across geological eras, life and time create each other in an endless recursive dance, neither reducible to the other, yet neither comprehensible in isolation. Life is what happens when time slows down enough to wonder. How do we measure the passage of time across the vast expanses of the cosmos? When we gaze at distant galaxies, we are not merely looking across space, but peering backward through time itself. The finite speed of light, traveling at 300,000 kilometers per second, means that astronomical observations always reveal the past, never the present. The farther we look, the deeper into cosmic history we see. This remarkable property of light transforms astronomy into a form of time travel, allowing us to directly observe the universe as it existed billions of years ago. The light from our sun takes about 8 minutes to reach Earth, meaning we see our star as it was 8 minutes in the past. Light from the nearest star beyond our sun, Proxima Centauri, takes 4.2 years to arrive. So we observe it as it was when that light began its journey. The nearest large galaxy to our Milky Way, the Andromeda Galaxy, appears to us as it was 2.5 million years ago, when our early human ancestors were just beginning to use stone tools. And the most distant galaxies visible with our most powerful telescopes show us the universe as it appeared more than 13 billion years in the past, just a few 100 million years after the Big Bang itself. This connection between distance and time allows astronomers to construct a cosmic timeline by observing objects at different distances. By studying galaxies billions of light years away, we can directly observe how the universe appeared in its youth, witnessing the evolution of cosmic structure across the eons. This remarkable capacity to see the past directly, rather than having to infer it from present conditions, gives astronomy a unique status among the sciences. But this window into cosmic history comes with significant challenges. To understand the universe's timeline, astronomers must accurately measure the distances to celestial objects, a task that has proven extraordinarily difficult throughout the history of astronomy. Unlike laboratory scientists, who can directly measure their subjects with rulers or calipers, astronomers must deduce vast cosmic distances using subtle clues gleaned from the light that reaches our telescopes. The quest to measure cosmic distances began with parallax, the apparent shift in an object's position when viewed from different perspectives. By observing nearby stars from opposite sides of Earth's orbit around the Sun, astronomers could detect tiny shifts in the star's apparent positions against the background of more distant stars. These shifts, often measuring mere fractions of an arcsecond, allowed the first reliable measurements of stellar distances in the 19th century. Parallax remains the most fundamental method of cosmic distance measurement, but it becomes impractical beyond a few thousand light years. To measure greater distances, astronomers have developed a ladder of techniques, each rung extending our reach further into the cosmos while depending on the calibration provided by the previous methods. One crucial rung on this cosmic distance ladder is the period-luminosity relationship of Cepheid variable stars, discovered by Henrietta Swan Leavitt in the early 20th century. Cepheids are pulsating stars that change in brightness with extremely regular periods ranging from days to months. Leavitt discovered that the intrinsic brightness of these stars correlates directly with their pulsation period, the brighter Cepheids having longer periods. This relationship transformed Cepheids into cosmic yardsticks. By measuring a Cepheid's pulsation period, astronomers could determine its intrinsic brightness. By comparing this intrinsic brightness with the star's apparent brightness as seen from Earth, they could calculate its distance using the inverse square law of light propagation. This technique allowed Edwin Hubble to prove in the 1920s that the spiral nebulae observed in the sky were actually distant galaxies far beyond our Milky Way, dramatically expanding our conception of the universe. For even greater distances, astronomers rely on type Ia supernovae, the catastrophic explosions of white dwarf stars that have accreted matter from companion stars until reaching a critical mass. These explosions release remarkably consistent amounts of energy, making them excellent standard candles visible across billions of light years. By carefully measuring the apparent brightness of these supernovae, astronomers can determine the distances to their host galaxies with considerable precision. These distance measurements, combined with observations of how light from distant objects is stretched toward longer wavelengths by the expansion of space, allow astronomers to establish a cosmic timeline. This redshift, as the stretching is called, increases with distance, revealing that more distant galaxies are moving away from us more rapidly than closer ones, a pattern consistent with a universe that began in a hot, dense state and has been expanding ever since. By measuring both distances and redshifts for large numbers of galaxies, astronomers have determined that the universe is approximately 13.8 billion years old, with an uncertainty of less than 1%. This remarkable precision in dating the cosmos represents one of the crowning achievements of modern science, allowing us to place ourselves within a precisely calibrated cosmic history. This cosmic timeline reveals a universe that has evolved dramatically over its history. The earliest epoch we can directly observe, the cosmic microwave background radiation, shows the universe as it appeared about 380,000 years after the Big Bang, when it had cooled enough for electrons and protons to combine into hydrogen atoms, allowing light to travel freely through space for the first time. After this era of recombination came the cosmic dark ages, a period lasting hundreds of millions of years when the universe contained no stars or galaxies, just a diffuse fog of neutral hydrogen and helium gas, gradually condensing under the influence of gravity. This period ended with the formation of the first stars and galaxies, which began to reionize the intergalactic medium, creating bubbles of ionized gas that eventually merged to transform the universe into the largely transparent state we observe today. The peak of star formation in the universe occurred roughly 10 billion years ago, during the epoch astronomers call cosmic noon. During this period, the average galaxy formed stars at rates 10 to 100 times higher than we observe in similar galaxies today. Since then, the cosmic star formation rate has declined steadily, with the universe entering a more quiescent phase as it ages. Large galaxy clusters, the most massive gravitationally bound structures in the universe, formed gradually through the hierarchical merging of smaller groups and clusters. The oldest massive clusters we observe formed about 10 billion years ago, though smaller collections of galaxies existed earlier. These clusters continue to grow today through the accretion of galaxies and groups along filamentary structures, a process we can observe in various stages by looking at clusters at different distances and therefore different cosmic epochs. The Sun and our solar system formed relatively late in cosmic history, about 4.6 billion years ago, roughly 9 billion years after the Big Bang. Earth and the other planets coalesced from the disk of gas and dust orbiting the young Sun, with Earth reaching approximately its current size within about 100 million years. The oldest known rocks on Earth's surface are about 4 billion years old, though the planet itself is older, with its early history obscured by the constant recycling of crustal rocks through plate tectonics. The earliest evidence of life on Earth dates to about 3.5 billion years ago, though some controversial findings suggest it might have appeared even earlier. Complex multicellular life became abundant only much more recently, about 540 million years ago during the Cambrian explosion. The evolution of life has been punctuated by mass extinction events, the most severe of which, the Permian-Triassic extinction about 252 million years ago, eliminated approximately 90% of all marine species and 70% of terrestrial vertebrate species. Mammals became the dominant land vertebrates only after the extinction of non-avian dinosaurs 66 million years ago. Human ancestors diverged from other apes about 6 million years ago, with anatomically modern humans emerging in Africa about 300,000 years ago. The development of agriculture began a mere 12,000 years ago, with recorded history extending back only about 5,000 years, a tiny fraction of cosmic history. This cosmic chronology, pieced together through astronomical observations, geological evidence, paleontology, and archaeological findings, places human existence within the broader context of universal time. We exist at a specific moment in cosmic evolution, when the universe has cooled enough for complex structures to form, but still contains sufficient free energy to power the processes of life and consciousness. Beyond these historical measurements, astronomers also use various celestial phenomena as cosmic clocks, tracking the passage of time across the universe. Pulsars, rapidly rotating neutron stars that emit beams of radiation from their magnetic poles, serve as extraordinarily precise timepieces. As these dense stellar remnants spin, their beams sweep across Earth like cosmic lighthouses, producing regular pulses of radio waves that can be measured with nanosecond precision. The most stable pulsars, called millisecond pulsars, have rotational periods that remain constant to within 1 part in 10 to the 15th power, rivaling the precision of atomic clocks. By monitoring arrays of these pulsars across the sky, astronomers create a galactic timing network that can detect subtle distortions in spacetime caused by passing gravitational waves, ripples in the fabric of spacetime, predicted by Einstein's general theory of relativity and first directly detected in 2016. Quasars, the extraordinarily bright cores of distant galaxies powered by supermassive black holes, provide another form of cosmic timekeeper. The flickering brightness of these objects, caused by processes in the accretion disks feeding their central black holes, follows patterns that appear stretched in time when observed from Earth due to cosmic expansion. By comparing the timescales of similar fluctuations in quasars at different distances, astronomers can directly measure the expansion history of the universe, confirming its acceleration and constraining models of dark energy, the mysterious force driving this acceleration. Even the cosmic microwave background radiation, the afterglow of the Big Bang itself, serves as a form of cosmic clock. The precise pattern of temperature fluctuations in this radiation encodes information about the age and composition of the universe, allowing astronomers to determine that 13.8 billion years have passed since the universe became transparent to radiation, with an uncertainty of less than 1%. The decay of radioactive isotopes provides yet another method for measuring cosmic time. When elements heavier than iron are created in supernova explosions or neutron star mergers, they include unstable isotopes that decay at precise, unchanging rates. By measuring the relative abundances of these isotopes and their decay products in meteorites, astronomers can determine when these elements were synthesized, providing an independent measure of the age of our solar system that agrees remarkably well with other dating methods. These diverse techniques for measuring cosmic time rely on the remarkable constancy of fundamental physical processes across the universe. The period of a Cepheid variable star depends on the physics of stellar pulsation, which in turn depends on nuclear reaction rates, gravitational forces, and the laws of thermodynamics. The consistency of type Ia supernovae as standard candles reflects the uniform physics of degenerate matter in white dwarf stars. The regularity of pulsar rotations depends on the conservation of angular momentum in extremely dense stars governed by quantum mechanics and general relativity. This consistency of physical law across space and time provides the foundation for our ability to measure cosmic history. If the laws of physics varied significantly from place to place or time to time, our cosmic clocks would be unreliable and our understanding of universal history would crumble. The success of our cosmological measurements thus provides powerful evidence for the universality of physical law, one of the fundamental assumptions of modern science. Yet measuring time across the universe involves subtle complexities beyond the simple ticking of cosmic clocks. Einstein's theories of relativity reveal that time itself flows at different rates depending on gravity and relative motion. Clocks in strong gravitational fields tick more slowly than those in weaker fields, and clocks in relative motion experience time dilation effects that must be carefully accounted for in precise measurements. These relativistic effects become significant when measuring time across astronomical distances. The GPS satellites orbiting Earth must correct for both the weaker gravity they experience compared to Earth's surface and their orbital velocity to maintain accurate timekeeping. Similarly, astronomical observations must account for the varying gravitational fields through which light travels on its journey from distant objects to our telescopes. Even more fundamentally, the expansion of the universe itself affects our perception of time in the cosmos. As space expands, it stretches not only the wavelengths of light, but also the apparent timescales of distant processes. A process that takes 1 year in a distant galaxy might appear to us to take 2 years if we observe it when the universe was half its current size, an effect astronomers call cosmological time dilation. This time dilation has been directly observed in the light curves of distant supernovae, which appear stretched compared to those of nearby supernovae. The rate at which a supernova brightens and then fades depends on physical processes within the exploding star, and when observed across billions of light years, these processes appear to unfold in slow motion due to the expansion of space itself. The concept of look-back time, the difference between the age of the universe now and the age of the universe when the light we observe was emitted, provides a framework for understanding our view into cosmic history. When we observe a galaxy 10 billion light-years away, we are seeing it as it existed when the universe was about 3.8 billion years old, a look-back time of 10 billion years. This look-back time creates a fundamental limitation in astronomy, a cosmic horizon beyond which we cannot see. Light from regions more distant than about 46 billion light-years cannot have reached us yet, even though the universe is only 13.8 billion years old, because the expansion of space itself has carried these regions beyond our observable universe. This horizon represents the limit of our ability to directly measure cosmic time through observation. Despite these challenges and limitations, the measurement of time across the cosmos has revealed a universe with a rich, comprehensible history, unfolding according to consistent physical laws. From the afterglow of the Big Bang to the formation of galaxies, from the birth and death of stars to the emergence of planets and life, we can trace a coherent narrative of cosmic evolution through time, placing our own existence within this grand universal context. This cosmic perspective transforms our understanding of time itself. No longer merely a local phenomenon measured by the rotation of our planet or the oscillations of atoms, time becomes a dimension woven into the very fabric of the cosmos, a dimension along which the universe evolves from simplicity toward complexity, from near-perfect uniformity toward the rich structure we observe today. The finite speed of light, often considered a limitation in our exploration of the cosmos, becomes instead a profound gift, allowing us to directly observe earlier epochs in the universe's history rather than having to infer them from present conditions. This direct window into the past gives astronomy a unique status among the sciences, enabling us to test our cosmological theories against observations of the early universe itself. As we continue to refine our techniques for measuring cosmic time, from the development of more precise atomic clocks to the deployment of gravitational wave observatories that can detect the subtle ripples in space-time caused by colliding black holes and neutron stars, our ability to chart the universe's history and future will only improve. Each advance in precision reveals new aspects of cosmic evolution, from the formation of the first stars to the nature of dark energy accelerating the universe's expansion. In the end, our ability to measure time across the universe reflects one of humanity's greatest intellectual achievements, the development of a coherent understanding of cosmic history based on careful observation and mathematical analysis. Through this understanding, we transcend the limitations of our brief individual lives and fleeting civilizational moment, connecting ourselves to the grand temporal sweep of universal evolution. To see far is to see the past. The universe tells its story through light and time. What becomes of time in the cosmic future? As we trace the possible trajectories of our universe forward through eons yet to unfold, we encounter profound questions about the ultimate fate of time itself. Will time continue flowing indefinitely into an endless future? Might it someday cease to have meaning in a universe devoid of change? Could time's arrow eventually reverse, or might time end altogether? In this chapter, we explore these questions, following the threads of current physics into the deep cosmic future where time's destiny awaits. Our exploration begins with the observed expansion of the universe. Since its discovery by Edwin Hubble in the 1920s, this expansion has been confirmed with increasing precision by generations of astronomers. Galaxies are moving away from each other as space itself stretches, carrying them along in its cosmic flow. The most distant galaxies recede the fastest, their light stretched toward the red end of the spectrum proportionally to their distance, creating the pattern we call Hubble's law. For decades, physicists expected this expansion to gradually slow due to the mutual gravitational attraction of all matter in the cosmos. The universe might eventually halt its expansion and collapse into a big crunch, or it might expand forever at an ever-decreasing rate, asymptotically approaching, but never quite reaching a static state. Either scenario would have profound implications for the future of time. But observations in the late 1990s revealed a shocking truth. The expansion of the universe is not slowing down at all. Instead, it is accelerating, with galaxies flying apart at an ever-increasing rate. This discovery, which earned the 2011 Nobel Prize in Physics, fundamentally changed our understanding of cosmic destiny and, consequently, the future of time. This cosmic acceleration appears to be driven by dark energy, a mysterious form of energy permeating all of space, comprising about 68% of the total energy content of the universe. Unlike matter, which becomes more diffuse as space expands, dark energy maintains a constant density, causing its influence to grow stronger relative to gravity as the universe expands. If dark energy maintains its current properties, as most observations suggest, the universe faces a future of eternal, accelerating expansion. This scenario, called the Big Freeze or heat death, presents a stark vision of time's future, one in which meaningful change eventually ceases even as time itself continues. In this scenario, the expansion of space will progressively isolate gravitationally bound structures from one another. In about 150 billion years, all galaxies beyond our local group will recede beyond our cosmic horizon, their light too redshifted by expanding space to ever reach us again. The observable universe will shrink to encompass only those galaxies gravitationally bound to our own Milky Way, primarily the Andromeda Galaxy and various smaller satellite galaxies. The Milky Way and Andromeda galaxies will merge in approximately 4.5 billion years, forming a single elliptical galaxy, sometimes called Milkomeda. Star formation within this merged galaxy will continue for perhaps another trillion years, but eventually the supply of gas for making new stars will be exhausted. The era of star formation will end, leaving existing stars to gradually burn through their nuclear fuel and die. One by one, stars will exhaust their hydrogen, swell into red giants, and then shed their outer layers, leaving behind cooling stellar remnants. The smallest red dwarf stars, with about 10% of the Sun's mass, will be the longest lived, continuing to shine dimly for up to 10 trillion years. But eventually, even these miserly stars will consume their last hydrogen atoms, and the universe will go dark. The stellar remnants left behind, primarily white dwarfs, neutron stars, and black holes, will continue to orbit within galaxies for incomprehensibly long periods. Over time, scales of 1 quadrillion to 100 quadrillion years. Gravitational interactions between these remnants will cause many to be ejected from galaxies, while others spiral inward towards central supermassive black holes. Black holes themselves will become the dominant celestial objects in this far future universe. But even these seemingly eternal engines of gravity are not truly permanent. In 1974, Stephen Hawking showed that black holes actually emit radiation through a quantum mechanical process, now called Hawking radiation. This emission causes black holes to lose mass extremely slowly, eventually evaporating entirely. For a black hole with the mass of our Sun, this evaporation would take about 10 to the power of 67 years, an almost unimaginably long time. Supermassive black holes at galactic centers with millions or billions of times the Sun's mass would last even longer, up to 10 to the power of 100 years. But in the infinite sweep of time, even these intervals are finite. Eventually, all black holes will evaporate, leaving behind only their radiated energy, now stretched to enormous wavelengths by the continuing expansion of space. What remains after the last black hole evaporates? A universe of extremely low density, filled with photons, neutrinos, and other fundamental particles, all separated by vast and ever-increasing distances. The temperature will approach absolute zero as radiation wavelengths stretch toward infinity. No complex structures will remain, no stars, no planets, no life. Even atoms will eventually disintegrate, as proton decay, predicted by some theories of particle physics, gradually converts matter into radiation over timescales of 10 to the power of 36 years or longer. In this far future state, time as we understand it becomes problematic. With no cycles, rhythms, or meaningful changes to mark its passage, time loses its familiar character. No clocks could function in such a universe. No processes could serve as temporal references. Time would continue as a dimension, but without change to give it meaning, it would become almost a formality, an empty coordinate with no observable significance. This scenario represents what physicists call the heat death of the universe, though ironically it is characterized by extreme cold rather than heat. The name refers to the thermodynamic concept of heat death, a state of maximum entropy where no free energy remains available to do work or drive processes. The universe would reach a state of perfect uniformity and equilibrium, a changeless eternity of darkness and silence. Yet even in this seemingly final state, quantum mechanics introduces an element of uncertainty. According to quantum theory, empty space is never truly empty, but constantly fluctuates with virtual particles appearing and disappearing. In the vast timescales of the far future, extremely rare quantum fluctuations might occasionally produce complex structures through sheer chance, a phenomenon called a Boltzmann brane. These hypothetical structures, potentially including conscious entities, would be vanishingly improbable, requiring fluctuations so rare they might occur only once in time spans vastly exceeding the current age of the universe. But in an eternal universe, even the most improbable events eventually occur. This suggests a strange future where time continues indefinitely, punctuated by isolated ephemeral islands of complexity in an otherwise dead cosmos. Some physicists have suggested even more exotic possibilities for the future of time. If dark energy is not constant but changes over time, a property described by a parameter called phantom energy, the universe might eventually undergo a big rip, where the accelerating expansion becomes so extreme that it tears apart all structures down to the subatomic level. In this scenario, the fabric of space-time itself would eventually be stretched beyond its limits, possibly ending time altogether, or perhaps initiating a transition to an entirely different cosmological framework. The big rip would occur when the scale factor of the universe becomes infinite in a finite amount of time, estimated in some models to be about 20 billion years from now. Alternatively, if dark energy weakens over time or even changes sign, becoming attractive rather than repulsive, the universe's expansion could halt and reverse, leading to a big crunch where all matter reconverges in a state similar to the Big Bang. This scenario raises the fascinating possibility of time reversing its arrow as entropy decreases during the contraction phase, though most physicists believe entropy would continue to increase even during a cosmic collapse. A big crunch might not represent the end of time, but rather a transition to a new phase. Some theories suggest that a contracting universe could bounce back into expansion, creating a cyclic model where big bangs and big crunches alternate indefinitely. In such a model, time might continue forever through successive cosmic cycles, each with its own arrow of time aligned with increasing entropy. Other speculative theories suggest more radical possibilities. String theory and its extensions propose that our universe might be one membrane or brane in a higher dimensional multiverse. Interactions between these branes might trigger new big bangs, either destroying our universe or spawning new ones while leaving ours intact. In such scenarios, time in our universe might end abruptly, or might continue alongside new timelines in other universes, creating a complex branching structure of temporal evolution. Quantum gravity theories suggest even more profound reconsiderations of time's nature and future. Loop quantum gravity, for instance, proposes that space-time itself has a discrete granular structure at the smallest scales. In some versions of this theory, what appears as the end of time in one phase might connect to the beginning of time in another phase, with the apparently singular moments of the Big Bang and potential Big Crunch actually representing smooth transitions in a more fundamental description of reality. The Wheeler-DeWitt equation, an attempt to apply quantum mechanics to the entire universe, suggests that at the most fundamental level, the universe might be timeless, with our experience of temporal flow emerging only at larger scales as an approximate description. If this timelessness is fundamental, then questions about the future of time might be misconceived. Time might not end or continue forever, but might simply be an emergent feature of reality that applies within certain domains and not others. These speculative frameworks remain unconfirmed, but they illustrate the profound questions about time's future that arise at the intersection of cosmology, quantum mechanics, and gravity. Our current physical theories approach their limits when projected into the distant future, suggesting that new physics might be needed to fully understand time's ultimate destiny. Amid these cosmic speculations, we should not forget the nearer future of time, the changes likely to occur over the next billions of years, rather than trillions or googles. On this more modest scale, the Sun will exhaust its core hydrogen in about 5 billion years, swelling into a red giant that may engulf Earth's orbit. Long before this, in about 1 billion years, the Sun's increasing luminosity will likely make Earth uninhabitable for complex life, as oceans evaporate and a runaway greenhouse effect takes hold. These solar changes represent a fundamental temporal limit for Earth-based life, establishing a deadline for either extinction or cosmic migration. If humanity, or its evolutionary or technological descendants, survive these challenges, they might spread to other star systems, potentially extending the time span of consciousness in the universe. But even such extended intelligence would eventually face the limits imposed by the heat death of the universe, the evaporation of black holes, and the eventual cessation of all complex processes. The finite nature of stellar and planetary timescales creates a temporal window for the phenomenon of consciousness, a span within which the universe has cooled enough for complex structures to form, but remains energetic enough to power information processing. We exist during a specific cosmic epoch when stars still shine, planets still orbit, and complexity can still emerge and persist. This epoch will not last forever, giving our moment in cosmic time a certain preciousness and significance. How should we think about these vast timescales, stretching so far beyond human experience? The psychological present, the moment we experience as now, spans only a fraction of a second. Human civilization has existed for a few thousand years. Our species has walked Earth for a few 100,000 years. Yet we contemplate futures measured in billions, trillions, or even greater spans of years, temporal horizons so distant they challenge our capacity for comprehension. The philosopher Martin Heidegger suggested that human beings are uniquely temporal creatures, existing not merely in the present, but projecting themselves into the future through anticipation and into the past through memory. Our ability to contemplate the far future of time, to imagine cosmological scenarios long after our biological existence has ended, exemplifies this temporally extended consciousness. Through mathematics and physics, we transcend our brief individual lifespans to participate in the universal temporal drama. This transcendence takes on additional dimensions when we consider the possibility of post-biological intelligence. If humanity creates artificial general intelligence or merges with its technological creations, the resulting entities might operate on vastly different timescales than biological humans. An intelligence implemented in computer hardware might experience subjective time at rates thousands or millions of times faster than we do, potentially experiencing subjective eons in what we would consider brief intervals. Such beings might experience the universe very differently, perceiving as painfully slow processes that seem instantaneous to us, while finding meaningful patterns in changes too gradual for human perception. Their temporal experience might more closely match the cosmic timescales we struggle to comprehend, allowing them to more directly engage with the slow evolution of stars and galaxies. Conversely, by slowing their subjective experience, such intelligences might extend their effective lifespan enormously, experiencing subjective eons while consuming minimal energy, perhaps allowing them to persist far longer into the cooling, darkening future of the cosmos. Some physicists have proposed that maximum computational efficiency occurs at very low temperatures, suggesting that intelligence might operate most effectively in the later, colder phases of cosmic evolution. These speculations about future intelligence highlight the subjective dimension of time, the way temporal experience depends not just on the objective flow of cosmic time, but on the rate of information processing and the structure of consciousness. The future of time has both objective and subjective dimensions, encompassing both the physical evolution of the cosmos and the changing nature of the beings experiencing that evolution. Returning to the physical future of time, we confront perhaps the most profound question: does time have an end? In the heat-death scenario, time continues indefinitely, but becomes increasingly empty of events or meaningful change. In the Big Rip scenario, time might end abruptly as space-time itself is torn apart. In cyclic models, time continues through successive cosmic phases, potentially without end. In emergent models, time itself might dissolve back into more fundamental timeless structures from which it arose. The answer to this question depends partly on how we define time. If time is simply a dimension of cosmic structure, it might continue indefinitely, even without events to mark its passage. If time is defined through change and entropy increase, it might effectively end when the universe reaches maximum entropy and meaningful change ceases. If time emerges from more fundamental timeless processes, it might transition back into timelessness under appropriate conditions. Current physics cannot definitively resolve these questions, suggesting they might require new theoretical frameworks or even entirely new ways of thinking about time. The future of time remains one of the greatest mysteries in cosmology, a frontier where our most sophisticated theories approach their limits and may need to give way to deeper, as yet undiscovered principles. What seems increasingly clear is that time is not the simple, universal flow we intuitively perceive. Instead, it emerges from the complex interplay of entropy, gravity, quantum mechanics, and cosmic evolution. Its future depends on properties of dark energy we are still working to understand, on quantum gravitational effects we have yet to fully formulate, and potentially on the actions of intelligences that might eventually manipulate space-time itself. In contemplating the future of time, we engage with the deepest questions about the nature of reality and our place within it. We recognize both the vastness of cosmic temporal scales and the brief, precious window our consciousness occupies within that expanse. We see how time gives meaning to existence through change, complexity, and the unfolding of possibilities, even as it imposes limits through entropy and cosmic evolution. Whether time continues forever in a darkening universe, cycles through successive cosmic epochs, dissolves back into more fundamental structures, or follows some path we have yet to imagine, its story remains intimately connected with our own. We are creatures of time, our existence shaped by its flow, our consciousness giving meaning to its passage. As we gaze into the cosmic future, tracing time's possible paths through eons yet to unfold, we practice a form of temporal transcendence, extending our awareness beyond our brief individual lives into the grandest scales of cosmic evolution. In doing so, we participate in one of humanity's noblest endeavors, the quest to understand not just where we came from and who we are, but where we and our universe are going as time continues its relentless, mysterious flow. Time continues until nothing is left to measure it. What if time is not the simple, linear flow we typically imagine? What if, instead of progressing relentlessly from past to future in a straight line, time curves back upon itself, branches into multiple pathways, or cycles through recurring patterns? In this chapter, we explore alternative conceptions of time structure, from ancient cyclic cosmologies to modern scientific theories proposing closed time-like curves, multiple time dimensions, and cyclical universes. These perspectives invite us to reconsider our most fundamental assumptions about temporal reality and open our minds to the possibility that time may be stranger and more varied than we typically perceive. Cyclic models of time have deep roots in human thought, appearing in philosophical and religious traditions across many cultures. Ancient Hindu cosmology conceived of time as moving through vast cycles called kalpas, each spanning billions of years and comprising a complete cycle of universal creation, existence, destruction, and renewal. Similar cyclic conceptions appeared in ancient Greek thought, with philosophers like Empedocles proposing that the cosmos cycles eternally between periods of love and strife, combination and separation. These ancient cyclic cosmologies reflected observations of natural temporal cycles, from the daily rotation of Earth to the annual cycle of seasons, the monthly phases of the Moon, and the longer cycles of planetary motions and stellar patterns. In a world dominated by such recurring patterns, it seemed natural to extend this cyclicity to the cosmos as a whole, imagining that the entire universe might participate in a grand cycle of death and rebirth. Modern cosmology initially seemed to banish such cyclic thinking. The discovery of cosmic expansion and the formulation of Big Bang theory suggested a universe with a definite beginning that expands continuously into the future. Time appeared fundamentally linear rather than cyclic, with the cosmos evolving from an initial singularity toward an open future of endless expansion or eventual contraction into a big crunch. Yet even within this apparently linear framework, some physicists began to reconsider the possibility of cosmic cycles. In the 1930s, Richard Tolman explored oscillating universe models, where expansion would eventually halt and reverse, leading to a big crunch followed by another Big Bang, creating an endless sequence of cosmic expansions and contractions. This model faced challenges, particularly from the second law of thermodynamics, which suggested that entropy would increase from one cycle to the next, making each successive cycle longer than the previous one and implying a beginning to the entire sequence. More recently, physicists have developed more sophisticated cyclic models that attempt to address these challenges. Paul Steinhardt and Neil Turok proposed an ekpyrotic model in which our three-dimensional universe exists as a brane within a higher dimensional space. This brane periodically collides with a parallel brane, with each collision generating a hot Big Bang-like state that initiates a new cycle of cosmic evolution. In this model, entropy generated in each cycle can be diluted or exported to the higher dimensional bulk space, potentially allowing cycles to continue indefinitely without an overall beginning. Roger Penrose proposed an even more radical cyclic model called conformal cyclic cosmology. Penrose observed that the highly uniform, low-entropy early universe shares mathematical similarities with the maximally expanded, high-entropy far future universe predicted by conventional cosmology. He suggested that these states might actually be identified with each other, with the empty, cold state of the far future serving as the uniform initial conditions for a new cosmic cycle. In Penrose's model, when the universe reaches a state where all matter has decayed and all black holes have evaporated, leaving only massless particles like photons in an effectively infinite volume, this state becomes mathematically equivalent to the highly uniform initial state of another cosmic cycle. The transition between cycles involves a rescaling of size, with the infinitely large end state of one cycle becoming the infinitesimally small beginning of the next. This conformal transformation connects cycles without requiring a bouncing contraction phase, potentially allowing entropy to reset between cycles. These modern cyclic cosmologies remain speculative, but illustrate how cyclicity might be reconciled with the second law of thermodynamics and other established physical principles. They suggest that what appears as the beginning or end of time from within a single cycle might actually be a transition point in a much larger temporal pattern, with the arrow of time maintaining a consistent direction within each cycle while the cycles themselves repeat indefinitely. Beyond these cosmic cycles spanning billions or trillions of years, some theories suggest the possibility of closed time-like curves, paths through space-time that return to their starting points, not just in space, but also in time. While prohibited in conventional space-time, Kurt Gödel discovered in 1949 that certain solutions to Einstein's field equations of general relativity permit such closed loops in time, at least mathematically. Gödel's solution described a rotating universe where sufficiently rapid travel along a specific path would return the traveler to their temporal starting point, effectively creating a form of time travel into the past. While our actual universe does not match Gödel's rotating model, his work demonstrated that closed time-like curves are not obviously prohibited by the mathematics of general relativity, opening the door to serious theoretical consideration of time loops. Subsequent work has identified other configurations that might permit closed time-like curves, including rapidly rotating cylinders with infinite length, Tipler cylinders, certain wormhole geometries connecting different regions of spacetime, and cosmic strings, hypothetical one-dimensional defects in spacetime that might form during phase transitions in the early universe. Each of these exotic configurations would require improbable or even physically impossible conditions, such as negative energy densities or materials with tension exceeding their mass energy, but they illustrate the surprising flexibility of spacetime geometry within Einstein's theory. The potential existence of closed time-like curves raises profound questions about causality and the nature of time. If travel into the past were possible, apparent paradoxes could arise. The classic grandfather paradox asks what would happen if a time traveler went back and prevented their own grandfather from meeting their grandmother, seemingly preventing the time traveler's own birth and therefore the time travel that created the situation. Physicists and philosophers have proposed various resolutions to such paradoxes. The Novikov self-consistency principle suggests that only self-consistent time loops can exist, those where the past remains unchanged despite the time traveler's presence because their actions were always part of history. In this view, you could travel to the past but would be unable to change it in ways that create contradictions, as events would necessarily unfold to avoid paradoxes. Others have suggested that time travel might create branch points leading to parallel timelines, as in the many worlds interpretation of quantum mechanics. In this view, a time traveler journeying to the past would create a new branch of reality rather than changing their own past. The original timeline continues unaltered, while a new timeline diverges from the point of the traveler's arrival. Stephen Hawking proposed a more radical solution in his chronology protection conjecture, suggesting that the laws of physics simply prohibit closed time-like curves. Hawking argued that quantum effects would create infinite energy fluctuations near the event horizon of any time machine, effectively preventing its formation or operation. While not definitively proven, this conjecture aligns with our observation that time travel paradoxes do not seem to occur in our experience, despite the apparent allowance for closed time-like curves in classical general relativity. These theoretical explorations of time travel highlight tensions between different aspects of our physical understanding. Classical general relativity seems to permit time loops under certain conditions, while quantum field theory suggests mechanisms that might prevent them. This tension represents one of many areas where a complete theory of quantum gravity, unifying these frameworks, might provide more definitive answers about the possible structures of time. Beyond cycles and loops, some theoretical approaches suggest even more exotic temporal possibilities. Multiple time dimensions, if they existed, would create a temporal landscape far more complex than our familiar one-dimensional time. Just as two spatial dimensions allow for more complex movements than a single dimension, multiple time dimensions would permit a richer variety of temporal relations and processes. In a two-dimensional time, for instance, temporal positions would be specified by two coordinates rather than one. Objects could evolve along different temporal trajectories, potentially moving through one time dimension while remaining static in another. Events that appear simultaneous when projected onto one time axis might be separated when viewed along another temporal dimension. While multiple time dimensions create significant conceptual and mathematical challenges, including potential violations of causality and problems with energy conservation, they have been explored in some approaches to string theory and other attempts to unify fundamental physics. Itzhak Bars and others have developed two time physics models that attempt to reformulate physical laws in a space-time with 2 time dimensions and 4 spatial dimensions, with our conventional 4-dimensional space-time emerging as a shadow of this higher dimensional structure. These explorations of multiple time dimensions remain highly speculative, but illustrate the flexibility of mathematical physics in conceptualizing temporal structures beyond our everyday experience. They suggest that time as we know it might be just one aspect of a more complex temporal reality, much as a shadow represents a lower dimensional projection of a higher dimensional object. Another approach to alternative temporal structures comes from causal set theory, which reimagines space-time as a discrete collection of events connected by causal relationships rather than as a continuous manifold. In this view, fundamental reality consists not of points in a smooth space-time, but of events with definite causal relations, specifying which events can influence which others. This causal approach places temporal relationships at the foundation of physics, with the distinction between space-like and time-like separations emerging from the pattern of causal connections rather than being assumed from the start. The continuous space-time of general relativity emerges as an approximation of this more fundamental discrete causal structure, much as the apparently smooth flow of water emerges from the collective behavior of discrete water molecules. Causal set theory suggests that the seemingly fundamental distinction between past, present, and future might itself be an emergent feature rather than a basic aspect of reality. The flowing time we experience might arise from the accumulation of new events and causal relations, with the distinction between past and future reflecting the asymmetric structure of these causal connections rather than an intrinsic temporal directionality. These various alternative conceptions of time structure, from cosmic cycles to closed loops to multiple dimensions, invite us to question our intuitive understanding of temporal reality. They suggest that the apparently simple, linear flow of time we experience might be just one aspect of a more complex temporal landscape, much as the apparently flat surface of Earth represents one aspect of its actual spherical geometry. Indeed, the transition from a flat Earth conception to a spherical one provides an instructive analogy for thinking about alternative temporal structures. Just as early humans naturally conceived of Earth as flat based on their local experience, we naturally think of time as a simple linear flow based on our psychological experience. Just as recognizing Earth's spherical nature required transcending local observations to integrate evidence from larger scales, recognizing more complex temporal structures may require integrating evidence and theory beyond our immediate experience. Of course, alternative temporal structures face significant theoretical and observational challenges. Cyclic cosmologies must explain how entropy resets between cycles or how it accumulates without implying a beginning to the entire sequence. Closed time-like curves must contend with potential paradoxes and quantum effects that might prevent their formation. Multiple time dimensions create problems with causality and energy definition that must be resolved. Moreover, we have limited observational evidence for temporal structures beyond the linear flow of our everyday experience. While cosmological observations reveal the history of our universe back to shortly after the Big Bang, they do not directly show what, if anything, existed before this event. Similarly, while general relativity has been confirmed with extraordinary precision, the exotic space-time configurations that might permit closed time-like curves lie far beyond our current observational capabilities. Yet absence of evidence is not evidence of absence, particularly when dealing with scales and conditions so far from our everyday experience. The history of science contains many examples of phenomena that seemed implausible or unobservable until theoretical understanding and observational techniques advanced. Atoms, black holes, and gravitational waves all moved from theoretical speculation to observed reality as science progressed. Perhaps alternative temporal structures await similar validation as our understanding deepens. In the meantime, These speculative frameworks provide valuable conceptual tools for exploring the boundaries of our understanding. They remind us that our intuitions about time, shaped by our limited personal and cultural experience, may not capture the full richness of temporal reality. They encourage an intellectual humility about our temporal conceptions, while simultaneously celebrating the power of mathematics and physics to transcend the limitations of intuition. This balanced perspective recognizes that while our everyday experience of linear, flowing time captures an important aspect of reality, it may not represent the complete picture. Just as Newtonian physics accurately describes motion at everyday speeds, while giving way to relativity at higher velocities, our conventional understanding of time may be a limited case of a more comprehensive temporal framework that includes cycles, loops, or other structures beyond our typical perception. Some physicists have suggested that even our conventional distinction between past, present, and future might be less fundamental than it appears. In this view, the entire history of the universe exists as a collection of these nows, with our experience of time's flow arising from the connections between them rather than from an intrinsic temporal dimension. This perspective aligns with the block universe conception from relativity, where past, present, and future exist equally as regions of a four-dimensional space-time rather than coming into and out of existence as time flows. It suggests that our experience of now and of time flowing from past to future might be a psychological feature rather than a fundamental aspect of physical reality. Yet even if time as flowing present proves to be emergent rather than fundamental, the patterns it describes remain meaningful. The asymmetry between past and future, the accumulation of entropy, the formation of memories and records, all reflect real patterns in the physical world, regardless of whether we interpret them through the lens of flowing time or timeless relations. Perhaps the most profound implication of alternative temporal structures is that time itself might have a more complex topology than we typically assume. Just as Earth's surface has a spherical topology rather than an infinite plane, time might curve or connect in ways that transcend our linear conception. The beginning and end of time, concepts that seem distinct and separated by billions of years in our conventional understanding, might actually connect to form a closed loop or cycle. What appears as a unique cosmic beginning might be part of a recurring pattern extending beyond our observational horizon. The possibility of such complex temporal topologies reminds us that our location within the universe constrains our perspective on its structure. Just as ancient humans could not directly perceive Earth's spherical shape from their limited vantage point on its surface, we cannot directly perceive the complete structure of cosmic time from our limited vantage point within a single epoch. Our observations extend only so far into the past, and our theories extrapolate only so far into the future, leaving room for broader patterns that become apparent only when viewed from a larger perspective. This recognition invites a certain intellectual humility about our temporal conceptions, an acknowledgement that the structure of time might be richer and more complex than our theories currently capture. It encourages us to hold our models lightly, recognizing them as useful approximations rather than final truths, always subject to revision as our understanding deepens. At the same time, these explorations of alternative temporal structures showcase the remarkable power of human thought to transcend the limitations of direct experience. Through mathematics, physics, and conceptual analysis, we can contemplate temporal possibilities far beyond our everyday perception, exploring cycles spanning billions of years, loops that return to their starting points, or dimensions that lie perpendicular to our familiar time axis. This capacity for temporal imagination represents one of the most distinctive features of human consciousness. We can mentally project ourselves into the distant past or future, construct models of time that differ radically from our direct experience, and use these models to deepen our understanding of reality. In doing so, we participate in a uniquely human form of temporal transcendence, extending our awareness beyond the narrow window of our personal existence into the vast temporal landscape of cosmic possibility. As we contemplate these alternative temporal structures, from ancient cyclic cosmologies to modern theories of closed time-like curves and multiple time dimensions, we reconnect with a deep current of human thinking about time's nature. Throughout history, Humans have recognized patterns of recurrence alongside linear progression, circular returns alongside irreversible changes. The tension between these temporal patterns has inspired philosophical and scientific inquiry across cultures and eras. Perhaps time itself embodies this tension, incorporating both linear and cyclic aspects, both progressive and recurrent patterns, both irreversible flows and circular returns. Perhaps our universe unfolds through time in ways that transcend our simple categorizations, combining aspects of linearity and cyclicity in a complex temporal tapestry that we are only beginning to comprehend. Whatever the ultimate structure of time may be, our exploration of these possibilities enriches our understanding of the cosmos and our place within it. It reminds us that reality may be more varied and subtle than our everyday experience suggests, that the patterns we perceive at human scales may be part of larger structures that become apparent only when viewed from broader perspectives. In this spirit of open inquiry, we continue to explore the multiple possibilities of time's structure, from continuous flows to discrete events, from linear progressions to cyclic returns, from singular paths to branching alternatives. Each perspective offers insight into different aspects of temporal reality, contributing to our evolving understanding of this most fundamental dimension of experience. Perhaps time doesn't end. Perhaps it begins again from silence. Few concepts capture human imagination quite like time travel. From ancient myths of prophetic visions to modern science fiction, stories of journeys across centuries, we have long been fascinated by the possibility of visiting the past or witnessing the future. This universal appeal reflects something profound about human consciousness, our awareness of time's flow, and our desire to transcend its constraints. But is time travel merely fantasy, or might it have some basis in physical reality? In this chapter, we explore what modern physics tells us about the possibilities and limitations of time travel, separating scientific understanding from speculative imagination, while acknowledging the fascinating questions that arise where they intersect. Let us begin by recognizing that, in one sense, we are all time travelers, moving inexorably forward through time at the rate of 1 second per second. This ordinary temporal progression, while taken for granted in everyday experience, already contains subtle complexities revealed by Einstein's theories of relativity. As we have seen in earlier chapters, time does not flow at the same rate for all observers, but varies with relative motion and gravitational fields. These relativistic effects create a form of time travel that is not merely theoretical, but experimentally confirmed. Consider an astronaut who spends 6 months aboard the International Space Station, orbiting at 17,500 miles per hour. Upon returning to Earth, this space traveler will have aged very slightly less than those who remained on the planet, experiencing about 1/100th of a second less time due to both the station's velocity and its slightly weaker gravitational field. This minuscule difference, while imperceptible to human awareness, represents a genuine form of time dilation that has been precisely measured using atomic clocks. More dramatic time dilation would occur at higher speeds or in stronger gravitational fields. An astronaut who could somehow travel at 99.99% of the speed of light for 1 year, according to their own clock, would return to find that 50 years had passed on Earth. Similarly, an observer hovering near the event horizon of a black hole might experience just 1 hour, while years or even centuries elapse for distant observers, depending on their proximity to the horizon. These relativistic effects constitute a form of time travel into the future, allowing a traveler to experience less time than others, and thus effectively jump ahead in time relative to them. Importantly, this form of time travel does not violate causality or create paradoxes. The traveler moves continuously forward in time according to their own experience, simply at a different rate than others. They can witness a future they otherwise would not have lived to see, but they cannot return to their original time or change the course of events that unfolded in their absence. This one-way nature of relativistic time travel aligns with our intuitive sense that the future remains open to influence, while the past is fixed and unchangeable. Indeed, the most profound challenge of time travel arises not from journeys into the future, but from the possibility of traveling into the past, where paradoxes and causal loops might emerge. Is such backward time travel physically possible, or does nature enforce a strict one-way direction for temporal experience? Einstein's general theory of relativity, our most comprehensive framework for understanding gravity and spacetime, does not explicitly forbid travel into the past. As we explored in the previous chapter, certain solutions to Einstein's field equations permit closed time-like curves, paths through spacetime that return to their starting points in both space and time. A traveler following such a curve could theoretically arrive back at their temporal starting point or even earlier, effectively traveling into the past. The first such solution was discovered by mathematician Kurt Gödel in 1949. Gödel found that in a rotating universe with a specific mass distribution, space-time could curve in a way that would allow an observer to follow a path into their own past. While our actual universe does not match Gödel's rotating model, his work demonstrated that backward time travel is not inherently prohibited by the mathematics of general relativity. Subsequent research has identified other theoretical configurations that might permit closed time-like curves. Physicist Kip Thorne and his colleagues investigated whether wormholes, hypothetical tunnels connecting different regions of space-time, could be stabilized and manipulated to create pathways into the past. They found that such time-traveling wormholes would be mathematically consistent with general relativity, though they would require exotic matter with negative energy density to remain open, a requirement that may not be physically realizable. Other proposed mechanisms for backward time travel include cosmic strings, hypothetical one-dimensional defects in space-time that might form during phase transitions in the early universe. If two such strings passed close to each other at high velocities, they could create a region where closed time-like curves become possible. Similarly, rapidly rotating massive cylinders might, in theory, distort space-time enough to create paths into the past, an idea known as the Tipler cylinder after physicist Frank Tipler, who first described it. These theoretical possibilities come with significant physical challenges. Wormholes, if they exist at all, might be unstable and collapse before anything could pass through them. Cosmic strings have never been directly observed, though some researchers continue to search for their gravitational effects. Tipler cylinders would need to be infinitely long or made of materials with impossible properties. Each of these mechanisms requires conditions that may not be achievable, even with the most advanced future technology, much less with our current capabilities. Beyond these practical challenges lies a more fundamental question. If backward time travel were physically possible, how would nature prevent or resolve the paradoxes that might arise? The classic grandfather paradox asks what would happen if a time traveler went back and prevented their own grandfather from meeting their grandmother, seemingly creating a contradiction where the time traveler both exists to make the journey and doesn't exist because their grandparents never met. Physicists and philosophers have proposed various resolutions to such paradoxes. The Novikov self-consistency principle suggests that only consistent time loops can exist, those where events in the past remain compatible with the future that gives rise to them. According to this principle, a time traveler visiting the past would find themselves unable to change historical events in ways that would prevent their own time travel. Something would always happen to prevent paradoxical outcomes, maintaining the consistency of the timeline. This resolution preserves causality at the cost of what appears to be a limitation on free will. A time traveler might retain the subjective feeling of being able to make any choice, but would find that when attempting to create a paradox, circumstances would conspire to prevent the contradictory outcome. In Novikov's view, such conspiracies of circumstances would be enforced by the laws of physics themselves, which would only allow self-consistent loops to exist. An alternative resolution suggests that backward time travel might create new timeline branches rather than changing the original timeline. In this many worlds approach, a time traveler journeying to the past would emerge in a parallel reality that branches off from the original timeline at the point of their arrival. They could then act freely in this new branch without risk of paradox, since their actions would not affect the original timeline from which they came. This approach preserves both causality and free will, but requires a branching structure of reality. A third possibility, advocated by Stephen Hawking in his chronology protection conjecture, is that the laws of physics simply prohibit closed time-like curves, and therefore backward time travel. Hawking suggested that quantum effects would generate infinite energy fluctuations near any incipient time machine, effectively preventing its formation or operation. This conjecture, while not definitively proven, would resolve the paradox problem by making backward time travel physically impossible. The unresolved tension between general relativity, which seems to permit closed time-like curves under certain conditions, and quantum mechanics, which might prevent them through effects like Hawking's proposed mechanism, highlights one of the central challenges at the frontier of theoretical physics. A complete theory of quantum gravity, unifying these frameworks, might provide more definitive answers about the possibility of backward time travel. In the absence of such a unified theory, the status of backward time travel remains uncertain from a purely theoretical perspective. While no fundamental principle seems to absolutely forbid it, the physical requirements for creating closed time-like curves may be practically impossible to achieve, and quantum effects may ultimately prevent their formation, even in theory. The lack of observed time travelers from the future provides empirical support for the view that backward time travel remains in the realm of science fiction rather than science fact, though this absence does not constitute definitive proof of impossibility. Beyond these theoretical considerations lie the practical and philosophical implications of potential time travel. If backward time travel were possible, even in limited forms, it would profoundly reshape our understanding of history, causality, and free will. Events would no longer be fixed once they occurred, but might be subject to revision by future interventions. Cause and effect could form loops rather than chains, with effects potentially preceding their causes from some perspectives. Such considerations have inspired countless scientific and philosophical thought experiments, as well as rich veins of speculative fiction. G. Wells's pioneering novel The Time Machine to films like Back to the Future and television series like Doctor Who, creative explorations of time travel have helped us examine the paradoxes and possibilities that might arise if temporal constraints could be overcome. While most of these fictional portrayals take significant liberties with physics, they often capture profound philosophical questions about the nature of time, determinism, and human choice. Would knowledge of the future constrain our ability to change it, creating a self-fulfilling prophecy? Could small changes in the past cascade into dramatic alterations of the future, the so-called butterfly effect of chaos theory? If we could visit any time and place, what would this reveal about our values and desires? Such questions engage us because time travel serves as a powerful metaphor for more achievable forms of temporal transcendence. While we cannot physically return to the past, we revisit it through memory, historical research, and the study of ancient light from distant galaxies. While we cannot bodily leap into the future, we project ourselves there through imagination, planning, and scientific prediction. Time travel stories externalize these mental processes, turning internal temporal mobility into physical journeys across time. This metaphorical resonance may explain why time travel narratives appear across diverse cultures and historical periods, from ancient myths of prophetic dreams to modern scientific speculation about wormholes and closed time-like curves. The desire to transcend temporal limitations reflects something fundamental about human consciousness: our awareness of time's passage and our curiosity about what lies beyond our immediate temporal horizon. Even as theoretical physics suggests significant constraints on physical time travel, technology has created new forms of temporal experience that echo aspects of fictional time travel. Digital recording allows us to capture moments and revisit them with a fidelity unimaginable to previous generations. Virtual reality can recreate historical environments, allowing a form of perceptual time travel into reconstructed pasts. Simulation technology enables us to explore possible futures based on different initial conditions and choices. These technologies do not constitute literal time travel, of course, but they extend our temporal reach in ways that parallel fictional time machines. They allow us to preserve the past with unprecedented detail, to experience simulated versions of historical or future environments, and to explore counterfactual scenarios that diverge from actual history. In doing so, they fulfill some of the human desires that animate time travel fiction, even without breaking the physical laws that constrain actual temporal movement. Alongside these technological developments, theoretical work on the foundations of quantum mechanics has suggested intriguing connections between information, probability, and temporal direction. The many worlds interpretation of quantum mechanics, proposed by Hugh Everett III, suggests that all possible outcomes of quantum measurements actually occur in different branches of reality, creating a vast multiverse of parallel timelines. While not designed as a theory of time travel, the many worlds interpretation provides a framework where something resembling time travel might conceivably occur. If it were somehow possible to traverse between these parallel branches, one might visit worlds where historical events unfolded differently, effectively experiencing alternate timelines. Though currently in the realm of speculation, such cross-branch travel would share some features with fictional time travel, while avoiding the paradoxes of backward temporal movement within a single timeline. Similarly, recent work in quantum information theory has explored questions about the reversibility of quantum processes and the possibility of rewinding quantum states. While not equivalent to macroscopic time travel, these investigations probe the boundaries between past and future at the quantum level, suggesting that the temporal arrow might be more complex at fundamental scales than in our everyday experience. Even if physical time travel remains forever beyond our reach, the scientific exploration of its possibility enriches our understanding of time itself. By examining the theoretical requirements and limitations of time travel, physicists probe the structure of space-time, the relationship between quantum mechanics and gravity, and the foundations of causality in our universe. The very questions raised by time travel speculation help clarify the nature of time as we currently understand it. This clarification extends to philosophical conceptions of time as well. Debates about the metaphysical status of past and future events, the reality of temporal flow, and the openness of the future gain new dimensions when considered in light of time travel possibilities. Whether or not backward temporal movement proves physically possible, contemplating its implications helps us refine our thinking about time's fundamental nature. In this way, time travel serves as both an object of scientific inquiry and a conceptual tool for exploring temporal understanding more broadly. The limitations we discover in pursuing actual time travel reveal the structure of time itself, just as the boundary of a shape defines its form. By probing these boundaries, we deepen our appreciation for the temporal reality we inhabit, even if we cannot escape its fundamental constraints. What then can we conclude about time travel from our current scientific understanding? First, that relativistic effects allow a form of time dilation that constitutes limited one-way travel into the future, a phenomenon confirmed by precise measurements with atomic clocks. Second, that general relativity does not obviously prohibit closed time-like curves that might permit backward time travel, though their creation would require exotic conditions that may not be physically realizable. Third, that quantum effects might ultimately prevent the formation of closed time-like curves through mechanisms like those proposed in Hawking's chronology protection conjecture, though this remains to be definitively established. These conclusions leave us in a state of qualified uncertainty about the ultimate possibility of backward time travel. The door does not appear entirely closed from a theoretical perspective, but significant physical and conceptual obstacles suggest that if time travel is possible at all, it would require physics well beyond our current understanding and technology far exceeding our present capabilities. This uncertainty itself tells us something important about the nature of time and the state of contemporary physics. It reminds us that fundamental questions about temporal structure remain unresolved at the intersection of general relativity and quantum mechanics, awaiting a more comprehensive theoretical framework. It highlights the provisional nature of our current understanding, always subject to revision as new evidence and theoretical insights emerge. And it underscores the wonder of temporal reality, complex and subtle enough to sustain both serious scientific investigation and endless creative speculation. As we contemplate the possibilities and limitations of time travel, we participate in one of humanity's most distinctive activities, using our consciousness to transcend the immediate constraints of our temporal existence. Whether through scientific theory, philosophical reflection, or imaginative fiction, we extend our awareness beyond the present moment, connecting past, present, and future in a web of understanding that itself represents a form of temporal mobility. In this most fundamental sense, the human mind has always been a time machine, capable of moving through remembered pasts and anticipated futures, even as our bodies remain anchored in the present. Our scientific exploration of physical time travel possibilities extends this natural capacity, pushing the boundaries of temporal understanding ever outward, even if the ultimate dream of unrestricted movement through time remains beyond our grasp. If we could leave time, what would we see? What would we become? Why do we remember the past, but not the future? This seemingly simple question leads us into profound territory at the intersection of physics, neuroscience, and philosophy. Our conscious experience of time, with its apparent flow from past to future, stands among the most intimate yet mysterious aspects of human awareness. In this chapter, we explore the relationship between consciousness and time, examining how our minds construct the temporal dimension of experience. The subjective experience of time differs markedly from the objective temporal structures described by physics. While relativity and quantum mechanics present time as a dimension that may curve, dilate, or even dissolve at fundamental scales, our inner experience presents time as an ever-moving flow, carrying us from a fixed past through a vivid present toward an open future. This flow feels absolutely central to consciousness itself, so deeply woven into our awareness that we can hardly imagine experience without it. Einstein's theories of relativity suggest a block universe where past, present, and future exist on equal footing as regions of a four-dimensional space-time. In this view, often called eternalism, the cosmos exists all at once, with no objective distinction between past, present, and future moments. If Einstein was right, why do we experience this stubborn illusion of flowing time? One compelling explanation connects our temporal experience to the thermodynamic arrow of time, the universal tendency for entropy to increase. Our ability to remember the past, but not the future, aligns with this entropic arrow, reflecting the fact that records and memories can form only in the direction of increasing entropy. When we form a memory, we create physical changes in our brains, establishing neural patterns that correlate with past events. These memory formation processes increase entropy in our brains and the broader environment, consistent with the second law of thermodynamics. The asymmetry of our temporal awareness, with the past recorded in memory while the future remains open, may thus reflect the underlying asymmetry of entropy in our universe. The neuroscience of temporal perception adds further insights. Our experience of now does not correspond to a mathematical instant, but spans a brief duration, sometimes called the specious present, typically lasting a few hundred milliseconds. Within this temporal window, our brains integrate information from different sensory modalities despite their varying processing speeds, creating the impression of a unified present moment. This neural integration involves multiple brain regions working together. The cerebellum helps track precise timing for motor coordination. The basal ganglia contribute to our perception of duration and rhythm. The insular cortex plays a role in our awareness of time passing. The hippocampus and surrounding structures organize experiences into episodic memories that preserve temporal order. Together, these systems create our sense of existing within a flowing temporal sequence rather than a static moment. Our perception of duration depends not just on objective clock time, but on how we attend to and process events. The expression, "time flies when you're having fun," captures a psychological reality, as engaging activities that capture our attention seem to pass more quickly than boring or unpleasant ones. Similarly, novel or emotionally significant experiences tend to be remembered as having lasted longer than routine ones, even if they occupied the same amount of clock time. Some neuroscientists and philosophers have suggested that our sense of time's flow might emerge from the sequential nature of conscious processing. According to this view, consciousness itself consists of a series of integrated moments rather than a continuous stream, with each moment incorporating past states into an ever-evolving present. The apparent flow of time would then reflect the structure of awareness itself, with consciousness constantly integrating new information while maintaining continuity with previous states. Buddhist meditation practices cultivate awareness of the present moment, often revealing how our ordinary sense of temporal flow depends on habitual patterns of attention and thought. Through sustained mindfulness, practitioners sometimes report experiences where the usual sense of time passing dissolves, replaced by an expanded awareness of an eternal now. Similar atemporal experiences appear in mystical traditions across cultures, suggesting that our ordinary temporal perception represents just one possible configuration of consciousness. Such altered states of temporal awareness also occur in certain neurological conditions and under the influence of psychoactive substances. Patients with specific brain damage may experience disruptions in their sense of temporal sequence, where events seem disconnected from their usual chronological order. Some psychedelic substances create experiences where time seems to stop, loop, or fragment into discontinuous moments, further highlighting the constructed nature of our usual temporal perception. If our sense of flowing time does not directly reflect an objective feature of the physical world, might consciousness itself play a role in establishing or defining time's direction? Some philosophers have explored this possibility, suggesting that the asymmetry between past and future might be intimately connected to the structure of conscious experience, rather than existing independently of observers. A more radical proposal comes from certain interpretations of quantum mechanics that assign a special role to observation or consciousness. In the von Neumann-Wigner interpretation, consciousness causes the collapse of quantum wave functions, selecting definite outcomes from quantum superpositions. If correct, this would give consciousness a unique role in establishing the sequence of actual events from the field of quantum possibilities. The tension between subjective and objective perspectives on time echoes ancient philosophical debates. Parmenides argued that change and time were illusions, that reality was fundamentally timeless and unchanging. Heraclitus, by contrast, held that constant change represented the basic nature of existence, famously observing that one cannot step into the same river twice because new waters are always flowing through. Modern physics has not definitively resolved this ancient debate, but has transformed it in significant ways. The block universe interpretation of relativity seems to support a view where change is in some sense illusory, with all moments existing equally in a timeless whole. Yet quantum mechanics, with its probabilistic evolution and the apparent role of observation in selecting definite outcomes, suggests that reality unfolds through a process of becoming rather than existing complete and static. The emergence of consciousness itself might represent an example of genuine novelty arising through temporal processes. Consciousness appears to have evolved over billions of years, emerging from increasingly complex arrangements of matter as life developed nervous systems capable of self-representation and model building. This evolutionary history suggests that consciousness is not a timeless feature of reality, but a relatively recent development in cosmic history. If consciousness evolved within and through temporal processes, it would be unsurprising that our awareness carries this temporal orientation within its very structure. We remember the past, but not the future, because our consciousness evolved as a predictive system operating within the thermodynamic gradient established by the early universe's low entropy state. Our awareness of time's flow, however it relates to fundamental reality, plays an essential role in our existence as conscious beings. Our sense of personal identity depends on the continuity of memory and anticipation. Our ability to learn, adapt, and make meaningful choices relies on our perception of temporal sequence and causality. Our emotional and ethical lives presuppose a directional flow from past through present to future. Perhaps time has both objective and subjective aspects, neither reducible to the other. The physical dimension of time described by relativity and quantum mechanics provides the substrate within which consciousness emerges and operates. The lived experience of temporal flow, with its moving present and asymmetric awareness, shapes how conscious beings navigate and make meaning within that physical reality. As we reflect on the relationship between consciousness and time, we might consider whether the flow we experience represents a limitation of our awareness or one of its most profound insights. Perhaps our sense of being carried along by time captures something essential about reality that our abstract physical theories have yet to fully incorporate. Either way, our consciousness of time's passage remains one of the most intimate yet mysterious aspects of human experience, connecting us to the broader cosmic narrative while establishing our unique perspective within it. We exist as temporal beings in a universe where past, present, and future intertwine in ways that continue to challenge our understanding, even as they define our very mode of being. To be alive is to witness time, one breath at a time. The universe remembers. From the cosmic microwave background radiation that preserves the afterglow of the Big Bang to the fossil record encased in ancient stone, the cosmos is filled with traces of its past. These echoes of earlier epochs are not merely passive remnants, but active participants in cosmic evolution, shaping the present and future through their enduring influence. In this chapter, we explore how time functions as the universe's memory, preserving information about what has been while enabling the emergence of what will be. Memory, in its broadest sense, refers to the preservation of information across time. While we typically associate memory with conscious recall, any system that retains traces of its previous states possesses a form of memory. The universe itself demonstrates this capacity through countless physical processes that record and preserve information about past events. The most ancient memory in our observable universe is the cosmic microwave background radiation, the thermal afterglow of the Big Bang. This faint radiation shows us the universe as it appeared about 380,000 years after its birth, when it had cooled enough for electrons and protons to form atoms, allowing light to travel freely through space for the first time. The slight temperature variations in this radiation preserved the density fluctuations that eventually grew into the galaxies and galaxy clusters we observe today. Light itself serves as a cosmic memory system, carrying information across vast distances and times. When we observe a galaxy 10 billion light-years away, we see it not as it exists now, but as it appeared 10 billion years ago, when the universe was less than 4 billion years old. The finite speed of light transforms our telescopes into time machines, allowing us to directly observe earlier epochs in cosmic history, rather than merely inferring them from current conditions. Closer to home, Earth maintains its own memory systems. The geological record preserves evidence of our planet's evolution over billions of years. Sedimentary rocks form like pages in a book, each layer capturing conditions from a specific period. Ice cores from Antarctica and Greenland trap tiny air bubbles that preserve the atmospheric composition from thousands of years ago, allowing scientists to track how Earth's climate has changed over time. The fossil record represents one of the most dramatic forms of Earth's memory, preserving impressions of extinct life forms in stone. From microscopic bacteria to massive dinosaurs, these remains tell the evolutionary story of life on our planet, documenting the endless adaptations, extinctions, and innovations that have shaped the biosphere over billions of years. Living organisms themselves embody biological memory systems. The most fundamental is DNA, the molecular code that preserves and transmits genetic information across generations. The human genome contains approximately 3 billion base pairs, encoding not just the blueprint for building and maintaining a human body, but also a historical record of our evolutionary past. Comparative genomics reveals our kinship with all life on Earth, from the roughly 98% genetic similarity between humans and chimpanzees to the shared genetic foundations that connect us to the simplest bacteria. Human cultural memory transcends biological mechanisms, creating systems for preserving and transmitting information across generations. Language allows knowledge to be shared through oral traditions. Writing dramatically expanded humanity's collective memory, allowing precise information to be preserved for thousands of years. Modern digital technologies have further transformed our mnemonic capabilities, enabling the storage and retrieval of vast quantities of information with unprecedented fidelity. These diverse forms of memory share a common foundation in the physical properties of our universe. Each memory system depends on stable structures that can encode information persistently across time. Whether stored in electromagnetic waves, geological formations, molecular sequences, neural patterns, or electronic media, all memory requires physical substrates that resist the overall trend toward increasing entropy. This resistance is always temporary rather than permanent. Even the most durable memory systems eventually degrade. Stone monuments erode, manuscripts decay, digital media become corrupted, neural connections fade, and ultimately, even the protons in atomic nuclei may decay over unimaginably long timescales. Each form of memory exists within the broader context of the second law of thermodynamics, which ensures that perfect information preservation is impossible over infinite time. Yet, within this fundamental constraint, the universe demonstrates remarkable capacity for preserving information across vast durations. The cosmic microwave background has maintained its pattern of temperature fluctuations for nearly 14 billion years. geological and paleontological records preserve information for hundreds of millions or billions of years. Even human cultural artifacts can endure for thousands of years under favorable conditions. Memory in complex systems often involves not just passive preservation, but active processing of information. Living organisms don't simply store genetic information, but use it to build new structures and respond to environmental challenges. Human cultures don't merely accumulate knowledge, but interpret, reorganize, and apply it to create new understanding. The universe itself doesn't just preserve its past states, but builds upon them to generate increasing complexity over time. This creative aspect of memory highlights the deep connection between information preservation and the emergence of novelty. Memory provides the foundation for new developments by maintaining the structures and patterns from which new arrangements can arise. Without memory, each moment would exist in isolation, disconnected from what came before and unable to influence what comes after. The universe's capacity to remember creates the continuity that allows complexity to build upon itself across time. The universe's memory also provides the foundation for prediction and anticipation. By preserving information about past patterns and regularities, memory systems enable the prediction of future events based on observed precedents. This predictive capacity appears most obviously in conscious minds that explicitly model potential futures, but it also manifests in simpler systems that have evolved to anticipate recurring patterns, from plants that prepare for dawn before the sun rises to immune systems that prepare for pathogens they have previously encountered. Even physical laws themselves can be understood as a form of cosmic memory. The consistent behavior of matter and energy across time and space represents a kind of remembering, with particles and fields maintaining the same properties and relationships throughout cosmic history. The reliability of these patterns allows complex structures to develop, as they can count on the consistent behavior of their components across time. As conscious beings, we occupy a unique position in this informational cosmos. Through perception, memory, and understanding, we not only participate in the universe's memory systems, but can consciously access and interpret them. We can read the cosmic microwave background, decipher the fossil record, analyze ancient DNA, and study historical documents, reconstructing the universe's past far beyond the limits of our direct experience. This capacity for temporal extension through memory gives human consciousness a distinctive relationship to time. We exist not just in the immediate present, but in an extended now that incorporates remembered pasts and anticipated futures. Through this enlarged temporal awareness, we participate in the universe's memory processes more consciously than other known systems, preserving specific information across generations. As we contemplate our place in this remembering universe, we might consider that nothing is ever truly forgotten within the causal structure of reality. Every event leaves its mark, however subtle, on subsequent states of the cosmos. The butterfly's wing movement alters the atmosphere in ways that propagate outward. The photon absorbed by a leaf millions of years ago contributed to the energy stored in the fossil fuels that power modern civilization. The words of long-dead individuals continue to influence the thoughts and actions of the living. In this sense, the past never fully disappears but continues to exert its influence through the causal chains that connect all events across space-time. The universe remembers not because some external record is kept, but because each moment grows from all previous moments, incorporating their influence into its very structure. Time itself becomes the medium of this remembering, the dimension through which information propagates and preserves itself, even as it transforms into new forms. Even the stars remember. Time writes everything down. Time flows onward, an eternal river carrying all of existence in its current. From the first moments after the Big Bang to the distant future beyond imagining, it connects all events in an unbroken stream. Throughout our journey, we have glimpsed time's many faces, as the fabric of space-time, as entropy's arrow, as life's rhythm, as consciousness's canvas. We have peered into its quantum mysteries and relativistic distortions, traced its fingerprints in fossil records and starlight, and contemplated its ultimate fate in the cosmos. Yet for all our scientific understanding, time remains intimately personal. We experience it through heartbeats and breaths, through memories cherished and moments awaited. It gives shape to our lives, meaning to our choices, and context to our existence. As you drift towards sleep, remember that you are not merely in time but of it, a conscious moment in the universe's grand unfolding, witnessing reality's continuous transformation. The same cosmic processes that forged stars in their brilliance created the awareness that now contemplates them. Time never stops, and neither does wonder. From the smallest quantum fluctuation to the vastest cosmic epoch, from your first breath to your final thought, time carries us all, together, through the endless dance of becoming. Rest now, fellow traveler through time. Tomorrow awaits.